not that people started with postulates or got that final answer very early. No, it came very late. Mathematical foundations, invertible structure, all that. It came very late. It was built up mainly by mathematicians, von Hilbert, and others. I will try to give references on all this. I have to write in one place. So we are just trying out what comes to my mind, and we say let us take only XYZ because XYZ can give result. But that also runs into problem. If I know a position accurately, very precisely at the time t0, afterwards position is not very, we cannot measure, we cannot say that system has this position at the time t greater than t0 because the whole quantum mechanics is probabilistic. We can only say it has certain probability at certain time. In general, that is the situation. So taking XYZ alone to describe state result will not work, because if you can describe at one time, same thing should describe the state afterwards. It doesn't. So we give up this. So what is that next question we ask? So we say, alright, let us start with probabilities right from the beginning. We say that if we know the probability that position XYZ is in a particular volume, x and x plus delta x, this probability is the fundamental thing, and this should represent the state. The answer is almost yes. This does represent the state, but we go in quantum mechanics on us to deal with not with probabilities, but with probability amplitudes, whose squares will give you probability. So we deal with not the probabilities, we take the probabilities of this XYZ. I am taking one particular example. So we are almost there by taking probabilities, but we actually work with. So in some sense I can say this, that the state of a system is this. I am talking about one particle, we will generalize it. Probability of the probability amplitude of XYZ in a range. What is that range? Range is what I have written here. You have the volume, a small volume, delta V, and the small volume is at position x. So you give me what is the probability it can be here, what is the probability it can be here. You give me all these probabilities, and you give all the probability amplitudes, and that is what describes the state of the system in quantum mechanics, and this is almost the complete answer, full answer. And what is this probability amplitude? You can guess. Any guesses? You know in a different name. I am calling it probability amplitude. Yes. Wave function. This is just the wave function. So, for a single particle, if you give me the wave function psi x, I will erase this part now. It will not do it. So, what is the situation like for a single particle? This is the final situation. No more different, but the state of a point particle is described by probability amplitude of position being in the range x and x plus delta x. So you give me this probability for all positions. Everywhere you give, take a small one, what is the probability here. So this probability, if it is given, that describes the state of the system. And as you have guessed it right, you are already familiar with this object. This probability is the wave function. So if I have point particle, the wave function psi x modulus square it gives you this property that we are talking about. So this property amplitude that we are talking about is the wave function. So I will rephrase this. A point particle without spin is described by a function of x, which is probability amplitude for x being in a certain rate. So we can calculate probability. If you give me the wave function, then you want to know how do I calculate something at a later time. You ask for the laws of motion. So what are the laws of motion here? You have to ask for the laws of motion because we want to know what is happening at a later time. This is just a Schrodinger equation I will write in abstract notation. Or you can write a coordinate system. This will be some operator. So there will be an equation like this, and we know from other sources how do we fix this, what operator will come. That Dirac fixes by using a classical correspondence with classical equations. That's a little long story, I don't want to go into that. That they should be Hamiltonian. Basically, equations should look like classical equations in some limit. That limit is small h plus. So this operator, this is the law of motion. But I have called law of motion in classical mechanics. So in quantum mechanics, the law of motion is the Schrodinger equation. But please remember, quantum mechanics becomes a difficult subject because there are so many ways of doing quantum mechanics. Instead of giving this law of motion, you can give some other law of motion, matrix mechanics, Heisenberg equation. So there are several ways of doing quantum mechanics. Even in classical theory, there are several ways of doing it. So let us remember this, because let us not say that this is the only way we can write law of motion. So this is the law of motion. If you write a particular Hamiltonian, if I know harmonic oscillator, then I know the Hamiltonian. So that harmonic oscillator Hamiltonian is specific to the system. I have to look at the system and decide what the Hamiltonian is, put it in here, and then try to solve this equation, use the initial value of wave function, and get the wave function at finite times. This is running exactly parallel to what I have said for classical mechanics. So you know the wave function at any time, then wave function gives you all information about the system, and you can calculate anything that you want to ask, anything which is meaningful to ask. Because in quantum mechanics, lots of questions lose their meaning when you compare to classical mechanics. In classical mechanics, you can give a Q and P simultaneously. In quantum mechanics, you do not do that. So the questions that you ask in quantum mechanics are actually different. In quantum mechanics, you will ask what is the probability that position is in this range. You will not ask what is the value of x at time t. You will not ask what is the trajectory. There is no trajectory. Because even if at one time position has different value, at other times position will not have different value. Trajectory means at all times it should have different value of position and momentum, both, which is not possible in quantum mechanics. So in quantum mechanics, the idea of trajectories is meaningless. It's not there. It loses its meaning. There are lots of concepts in classical mechanics which lose their meaning, or they get modified when we come from classical to quantum mechanics. Alright, now, so we know the state of the system, we have talked about laws of motion, we have talked about the fact that the state determines a state at time t equal to 0, plus laws give you a state at time t. So let me write that. So we have the following situation: the state, if I know at time t 0, plus laws of motion or equations of motion. It gives you the information about state of at time t. At any time you can calculate what will be the state of the system. We have chosen to describe the state by wave function, so you can calculate wave function at any time. You can choose to describe state by something else. You can calculate corresponding thing at time. Now let us see what is the critical change here. What has happened? The main thing is you cannot have simultaneous very precise measurement of many things. Only certain things can be measured precisely, and only those things can come here in wave function. So for example, instead of starting with x, we have said that we can measure x, y, z very accurately, but we have to ask for probabilities, and probabilities are almost not good enough. You have to ask for amplitude for x, y, z in certain way. That is why we have written it. Okay. This is in quantum mechanics, but in classical mechanics we had other things. We had ST. So we can actually start with if somebody wants, and this is actually useful in Hamiltonian terms for certain kinds of problems, and we can repeat this process. And finally, the state will be described by a function of momentum, and that will be momentum space vector. You are, I suppose, everybody is familiar about momentum space vector. So you can have different things. In quantum mechanics, in classical mechanics, you can mix x and p and define new variables. Can I do here? The answer is yes. You can do there as long as they can be measured simultaneously. You can start with any variable x1, x2, x3 as long as they can be measured simultaneously. The crucial property is that what we take here and what comes here in the final wave functions x, y, z or p, x, p, y, p, z, those things, corresponding things, they should be, I should be able to measure them simultaneously. There should be no uncertainty relation. So that is a critical requirement. So in principle, we can start with any observable and repeat this process, what we have done. So you have a system, so identify x1, x2, xn, which can be measured simultaneously. How do we decide? We will see. Which can be. And then you can repeat this process. You need only probability amplitudes of these objects. Okay? But of course, how do you decide that they can be measured simultaneously or not? So there should be criteria, because original uncertainty principle is about position and momentum only. Now we are talking about general functions, capital X1, capital X2, capital Xn, which could be any function of position and momentum. So how do we decide? So that brings me to the following. Here we have to do two things. One, first of all, we have to say that Heisenberg, when we were doing intensities of spectral lines in 1926, he derived it correctly and got the correct answers. That is 1926. That is when matrix mechanics of Heisenberg was born. So early days, 26. I think we are working on intensities of the spectral lines. And he derived the answer correctly. There is a story about it, but I will not go into the story. He got the answers correctly, and before or after publication, sometime around that, I don't know exactly when, he sent his manuscript paper to Bonn and Jordan. He actually sent to Bonn, and Jordan was working with Max Bonn. Max Born and Jordan were working with that. He had an equation. I will show you that equation. Unfortunately, there is no side projection here. I will just circulate there. There is several other things. Immediate can it be set up? Oh, it is available. Then no problem. I will try to project. So can I project on my computer?
Yes, sir. Yes,
So,
sir.
so I arrange my things. I have to take out from different places. I will put them in one place and show all the states separately just for your interest and your references. The statement that I am making you can find there. So Max Born and so Heisenberg sent this paper to Max Born on this, and he derived the answers correctly. And what they realized was his one equation. They said this is a matrix equation, and that is where the position and momentum, they have become operators. Heisenberg did not know matrices, so he did not realize that he is now dealing with matrices. What were these matrices? They were matrix elements of position and momentum operator in our language, because he was working with periodic orbits and he took Fourier transform since he was considering the transition between two elements M and N. So he got results which require him to take Fourier transform of position and momentum with respect to time and frequencies with respect to two elements changing. So he wrote an equation, and that equation Max Born immediately realized it's a matrix equation. Then of course he worked on that matrix equation, and then what he gets is he understands that is the most important equation, and they use that equation in the following form which you will understand. That equation I will show you maybe some other time. That equation was just this matrix equation. I just got the diagonal element. Take MM element, so I 1. That equation was just this matrix multiplication of Q, P minus P, Q equal to 1. And that was the diagonal element. So then Born introduced canonical quantization. He was more of a mathematician, and also of course so many things others he done about physical intuition. So then Max Born, Jordan and Dirac, they used this successfully to quantize in particular very soon to quantize electromagnetic field and build whole quantum electrodynamics. And it was Dirac who also established the correspondence with classical mechanics that quasi-brackets should go to the observables become operators and quasi-brackets go to the corresponding form vectors. So I will summarize this now. So net effect of all this is that the observable quantities, coordinates, momenta, energy, angular momentum, anything you think of, in quantum mechanics they have to be treated as Hermitian operators. So about observables, these things happen. This is the one part. Observable means anything, position, momentum, energy, anything. Now, this particular thing it appears in several places. So, one place where it appears is that observables are quantized. Okay? So these operators, if you take eigenvalues of corresponding operator, get possible outcomes of the if you take quantity x, observable quantity x, measure it, all values are not allowed because the values are quantized. So how do I calculate? So the answer is somehow get hold of this operator, corresponding operator, calculate its eigenvalues. Operators are like matrices, so calculating eigenvalues, conceptually there is no difference. In practice, calculation may be very different. But conceptually, the eigenvalues for operators in a vector space the same as the matrices. There is no difference actually. So that is one thing which happens. It tells you what are the possible outcomes of measurement of energy. So get hold of energy operator, which we call Hamiltonian operator, calculate its eigenvalue, whichever way you like. Schrodinger calculated it by solving differential equation or hydrogen atom. Only calculated using just computational lessons. So there may be different ways. So if you take hydrogen atom, calculate the eigenvalues. These are the only allowed values of energy which you will see when you make a measurement of energy. That is one thing happens. The second information now we have to have is this. The operators are like matrices. Matrix product depends on the order you multiply. So same thing happens for operators. So if I have AB operators, there is no difference actually. This may or may not be equal to BA remainder. So we say they don't control. The commutator is 0. The commutator is defined by the commutator of two operators X AB is defined by this AB minus BA. So if the commutator is 0, then we say they commute, and then we have mathematical formulation which tells me that there will be no uncertainty. No uncertainty means so uncertainty still applies if the commutator is not 0. Then there will be uncertainty. So for our purpose here, we want to describe states. So we have to identify observables, somehow get hold of the corresponding operators, and those operators should have the property that they commute pairwise. They commute. Then all of them can be measured simultaneously. That is the state. Now, how do we get these operators? We have to see we have to do different things for different cases. So, but basic idea is just this. What we have said, what I have said here. That get hold of these observables and corresponding operators, which can be measured simultaneously, and therefore they commute. And therefore, that is the starting point for describing state of the system. Corresponding probability amplitudes will describe the system. Will be one way of describing the state of the system. I keep on saying one way because there are so many ways of describing the system in quantum mechanics. What we are discussing is one corner or one description, inverse description. Again, in that one way of describing the system. Alright. So we have learned how to describe the system. We also know that observables become Hermitian operators. Hermitian operator is a special property. We will talk about it separately. It ensures that they have the right. The corresponding operators have the right mathematical properties for consistent interpretation of probabilities. Now this requires an expansion, I understand, but we will not go to this. So these Hermitian operators, they have the right properties. Even definition I have not given. But for our purpose today, the eigenvalues of these operators they are the possible outcomes of the corresponding measurement, and if two operators commute, they can be measured simultaneously. Okay. So what else do we need? Let me try to think whether we have completed everything. And also let me try to briefly write here. We have talked about steps, and then we have talked about observable simultaneously that can be measured simultaneously. Then we have talked about the corresponding probability amplitude. So here we can have several any operators xn. So we want probability amplitudes for these operators. And if you like, we say that this is like this. Or this is not the whole story, we will continue, but this is correct and complete. If you don't want, you can stick to this. State of a quantum numerical system. So this is now complete. There is no if and buts or question marks here. But we'll change the language. We'll change it to a language which is more used, which is more commonly available and more useful for us. So as far as states are concerned, we are going to accept this and see what change in language is required, so that you understand from different books whatever is written there. Alright. Then we have statements about observables. See, remember classical mechanics, we had states, then observables. Observables we have. Observables are admission operators. As soon as they say operator or admission operator, that means there is some vector space somewhere. I will come to that. So I will put a small question mark to which vector. We cannot talk about we can probably talk about admission operators without vector spaces, but not admission operators. Let's not worry about that question. But there is some vector space in which we are trying to describe these operators. So what is the vector space? We have to consider. But given admission operators, we can formulate the equation of motion, which is basically what say. Let me say one thing. Instead of taking this probability amplitude to describe state, we can take an abstract object, some symbol only, and say that this will describe, provided we know the rules of calculating this. So this is some symbol. We call this a state vector. This is a choice. It is not compulsory. If you are comfortable with this, choose this. This is like bracket vector. If you want, you can stick to this. This is like wave function. So you can work with wave functions. You can work with bracket functions. So what I mean is following. Instead of working with probability amplitudes or all the wave functions, we can work with abstract objects, which will be some symbols, and there will be rules which will tell me how to calculate these probability amplitudes or anything that we want out here. So there will be rules like that we have to apply. So please remember this. So equations of motion are in that form. I across, here dt, here will be some symbol which I have used here, equal to some operator. All this can be made precise. Right now there are some things which are not making precise. So we have equation of motion, we have this, we also have this statement About operators, let if AB commutator is 0, then AB can be measured simultaneously. Okay. So far, I think you should follow everything. If you have questions, please ask. It is still not completed, but I am going to complete the rest of the story very soon. You can see whatever we had in classical dynamics is appearing in some form, laws of motion. The Hamiltonian has to be specified. Then only we can solve this equation. I should know whether what is the potential here. Then only we can solve this. So that is like specifying the force or interaction or Lagrangian. Yes, some questions anyone?
Ashok, when you mean by simultaneously measured, you mean that state is an eigenstate of both A and B, a particular eigenstate, and therefore measurement will not disturb the system.
Yeah, but I am not going into keeping.
No, but if I just say AB, I can have a combination of.
No, I still don't know what these AB's operators are. I still don't know how to calculate commutators. I am coming to that.
But then you said it can be measured. I can measure simultaneously.
No, that yes, what you are saying is 100% correct. But I am avoiding certain issues.
Oh.
I want to concentrate on what I need for spin, to set up a formula for spin. Okay? Maybe I will try to come back to your question after some time. See, my aim is not to explain this. My aim is to make them understand how I set up the formula for spin. What kind of a function is required and so on. How do I go about doing my business there? Okay? So now the question that I have not addressed so far is following. I have some object, some observable quantities. What is the corresponding operator? I don't know. And how do I calculate anything? How do I calculate eigenvalues? I don't know. I have not said anything. So two questions still remain in my discussion. By the way, Manisa, your question I have not addressed because I have not introduced vector spaces.
Okay.
I have kept vector spaces aside because some people have not exposure to vector spaces.
Okay.
Alright. So the question that these questions are not very parallel to what I have said for classical mechanics. But there are things which have to be set right before we can actually start. So what are the things? Given and observable. Let us follow what is the corresponding operator. This is very important. Without that, all whatever I have said has no meaning. I should know what is the corresponding operator. Given two things, x, y, I want to know whether they can be measured simultaneously. So I should be able to calculate commutator. I have not said anything how we calculate commutator. So given x, y, we have operator, some operator somewhere. How do we compute commutator? Then decide whether they can be measured simultaneously or not. Okay. I will give partial answer. Rest of the answer we will see when we come to spin. The simplest setting is you have a so let me try to give an answer which is complete but it is partial. Partial in the sense there are other systems where we have to do something else. So suppose I have a classical system. I can have generalized formula and any observable quantity is a function of Q and P. This part we have. When we go to quantum systems, we will have new things that we will see. But if I start with a system which is a classical system with which you are familiar, that will be described in terms of some generalized coordinates and generalized momentum, and any observable will be function of generalized coordinates and momentum. So then the rule is, suppose I know what 2p are. Suppose we know. Then the job is simple. It becomes operator in which we have replaced Ui operator Q and Qi operator Q. It is not as easy as it sounds, but okay, this is what we do. This is what we do in textbook quantum mechanics. But as you read here, he says, with all this you cannot calculate everything unless you know how some more information, how to multiply, what if you multiply in different orders, what happens. In particular, he says it is necessary to postulate some amount of computation relations. Okay, so that is, I will lay some words. So what I am going to write is known to you. You postulate, this is a presumption or postulate of quantum mechanics that the fundamental canonical pair of variables QP satisfy computation relation. So if you have a system, a classical system, I want to quantize, then these operators will become corresponding operators there, and the only information I am giving you is Dirac gives. I am not giving you anything. Dirac says there is Dirac model bomb rule, which I have state this. And once you have written down this data again, once you have this, you don't need anything more to calculate. This is it. So basically I have described to you postulates except one. One will come in the second part of my lecture, identical particles. Apart from identical particles, I have described the postulates in my way here. Okay. I will write down as postulates statements separately, so that you have the final answer. You don't have to remember all this blah blah blah. All this is only to motivate to arrive at this. Now, are you convinced that this is sufficient to calculate anything, eigenvalues or anything you want? Or you have doubts? If you have doubts, please ask. I will give examples where you can see there is nothing else is required. In fact, this is what Pauli did for hydrogen. Because Isaac and Pauli were friends, they were both students of Samarkand. So Heisenberg sent his papers to Pauli. Pauli criticized it heavily, and then Heisenberg retorted back something. Pauli was offended, he sat back and then he sat down and calculated. Hydrogen atoms were found in 1926 or 27, maybe I think 26 only. And he calculated hydrogen atom energy levels using only computation relations. That is original calculation is the Pauli. This is well known, given in some books. So what I mean is this computation relations are very powerful. After this you don't need anything else for calculating in principle. And hydrogen atom is not so common example. You know ladder operators in harmonic oscillators, you know ladder operators for angular momentum. So you use only ladder operators and computation relations to get the answers for eigenvalues of energies of harmonic oscillator and eigenvalues of angular momentum operators. So these are very powerful. The buck stops here. Now you can start calculating if you have enough technical knowledge. Otherwise, learn and start calculating. In principle, there is nothing more. Otherwise, there is another approach. Using the computation relations, you can set up a representation. Work in a vector space, set up a representation. Work in a representation, set up differential equation and solve the differential equation, which is what solving over there. When I say set up representation, that means instead of working with abstract objects, work with wave functions. Write the equation which will satisfy. That can be derived from here. And this equivalence was 2 by Schrodinger system. That matrix mechanics and Schrodinger mechanics are equivalent. They will give you the same answers. Okay. So what I mean is, if you are not very comfortable, in fact many cases, algebraic method using combination relations may not be the best way. Like chemistry, you have molecules, big molecules, these combination relations may be useless. They will transform into, they will start with the equation, put it on computer and solve it. So, but they have these combination relations all have all the necessary power and information that is needed to proceed with calculations. How you proceed will actually depend on what you know and what problem you want to solve. So this completes my way of introducing postulates of quantum mechanics. As I said, I will need to introduce one more postulate, which is about identical particles. Okay. I will write down all these postulates in a formal fashion, and you will see this is all that is there. Okay. Except one thing is missing, that is vector spaces. So that part I have to decide how much time I should spend or what all I have to do. I have to find out whether it will be covered in any other course or not. We will need some part of vector spaces, which I will try to do. So are there any questions so far? So the first postulate is about the state, second postulate is about observables being operators, the third postulate I have not discussed, how you calculate probabilities, and fourth postulate is the Schrodinger foundation relations, canonical quantization, fifth postulate is, let us say, dynamical equation, Schrodinger equation, and the last one is about identical particles, which we will discuss. Okay. Now I have not described one thing. What was it? I just forgot. Yeah, there is something important I want to tell you, which will be useful if you want to connect it with vector spaces. I would like to keep vector spaces away from, as much away from the regular course lectures as possible. That is, give a separate lecture on that rather than mix it up with what I am doing here. Okay? But let me give you some more things about what I have said. That is good. And this is about postulate 3 I have not mentioned. And that is where vector spaces come in big way. Without coming to vector spaces, it is very difficult to describe, but I will describe it for you in terms of wave function. And if you know the wave function, how do you calculate differences? Okay? So I will translate that vector space language in terms of wave functions. And I will say everything in terms of wave functions. You can also say same thing in terms of vector space language without talking about wave function, by talking about abstracted and block vectors. So this is the third postulate. This is the most important one, because whatever I have said is all theory on the blackboard. It may or may not have something to do with the experiment. But the third postulate connects the theory with the experiments. It tells you how do you calculate the quantities that you actually measure in an experiment. How do you calculate? What is the process? What are the assumptions? So I will describe the third postulate, which gives you the connection of theory with experiment. So because this is a bit long, I will describe in terms of wave function. So let us say we have some system. System can be one particle, any number of particles. It is being described by a wave function. So let us take our one particle here. This is a general system we may have, and this is one particle. Now, what is the property that this wave function should have, so that it is acceptable to describe a physical system. Now here I am going to give only the statements, no discussion, because you are familiar. So the first thing is, you basically, let me just introduce the idea of vector space. So we consider the set of all wave functions which are square integrable, that is square, modulus square, HKS, it is finite. This thing forms what is known as mathematical language a Hilbert space, but I will simply call it vector space. Because Hilbert space I should define, vector space I should define. So this is what is involved here in quantum mechanics. So this is vector space or Hilbert space for what part field. Here we don't know what is the Hilbert space. See, if I am working in abstract language, we don't know what is the Hilbert space to start with. So we have to have some idea about Hilbert space. We want to connect what we have done here in abstract system. Here you just write psi, or you will write in Dirac notation, you will write that the system is described by this some get vector, some symbol which is nothing more than a symbol plus some rules. So what are the properties? The properties of this define a vector space or Hilbert space. So those properties can be listed. Basically, I will tell you a few things, but not all. So you collect all elements and with certain properties so that it forms a vector space with a scalar product. So set up all these things, they should form. These are the rules of manipulating this vector space with a scalar product. Which means I should know what is meaning of taking superposition. We should know given two vectors, we should know what is this. We should also know what is scalar product of two vectors, which in Dirac notation is just this. So we should know how to calculate this, or what properties these objects have. So that will define a vector space. If I list all the properties, that will define a vector space with a scalar product. That is fairly standard, but I want you to concentrate on something else, which is what is relevant for me to discuss a spin. So the question is, say here we can describe wave function or talk about this. Imagine some totally new system. Imagine you have never learned quantum field theory. Quantum field theory, whatever we have done is there, but we don't know what is the Hilbert space. How do we get through the Hilbert space or vector space? So the answer is what I have said. Where do we start? So you look at observable quantities. Observable quantities means you look at the Hermitian operator. I am only giving the prescription because lot of vector space knowledge is required here. I am only giving prescription. So start with Hermitian operators and find x1, x2, xn, these operators such that they pairwise commute. When we have quantized the system, we know what the completion relations are, so we can check this. Okay? Suppose I am talking about quantum field theory, you all of you will not be aware of quantum field theory, but imagine a system which has certain dynamic, which has certain coordinates, momenta, we have quantized, so we know completion relations. There are certain operators which we can identify as Hermitian operators. To get hold of those Hermitian operators which commute. Take any two, they should commute. So they can be measured simultaneously. So they have physical connection. So get hold of this. And the property which Professor Nani was mentioning is, these things have an important property, that there will be simultaneous eigenvector for all of them. That is, I can find vector phi such that x1, this is an eigenvector of 5 with some value lambda 1, and it is an eigenvector of x2 also, x3 also, all of them. So we have to find commuting operators, simultaneous eigenvectors, take that as a basis, form a superposition that gives you the vector space in two sentences. So there is a way of constructing vector spaces, and this partly we will need for our skills, but let's see. So there is a way of constructing Hilbert space which works beyond what we do in quantum mechanics, which works beyond for experiments, which will work in quantum theory, which will work in any quantum field. Okay? That will be the procedure. But the kind of operators that you will have in different systems will be different. In field theory, these are number operators, for example. If anyone is familiar, you will know these are number operators. They have a different kind of interpretation. Alright, so coming back to this, what is that we have to do? I have given this flavor so that you, if at all we talk about vector spaces, you will do all this and we keep this in mind. Let me see whether we will have time or not. Yeah.
So, from a mathematical point of view, suppose if I have two operators, I can always check whether it commutes or not.
If you know certain fundamental combination relations, yeah. Like QP you have, when you have a classical system and when you quantize, you postulate certain fundamental combination relations. So if you know this, you should be able to calculate. Yes.
Then suppose A and B are the two operators. They have certain eigenstates, and B also have certain eigenstates. So you say that if they commute,
yeah.
they will have some simultaneous.
No, the correct statement is you can always have simultaneous eigenstates. You can always form simultaneous eigenstates which will form a basis, complete set. But suppose I take two operators and just find their eigenvectors, it may not happen that all of them are simultaneous eigenvectors. So that you have to make linear combinations, then you can make it, always.
I am asking that actually, how to form that simultaneous eigenvectors?
How do you?
For some known problems, we know that how to find out simultaneous eigenvectors. But in general, if I are given two operators,
So you don't have to form in most of the cases. Most of the cases, the statement that such a thing exists is sufficient. But if you really want to see example, I will fish out an example. I will give you two 4x4 matrices. I have an example in my laptop. I will give you two 4x4 matrices. They commute, and you can try your hand with that and try to find simultaneous eigenvectors. We will do that as an example.
So can you please repeat what you said? I want to listen to it.
My statement is, if I give two operators A and B, Hermitian operators, they commute. Okay? Now, if I find their eigenvectors, it is not necessary that they will be simultaneous eigenvectors.
Okay.
I may have to do extra work.
Yes.
This is in case of degeneracy, one of them being degenerate.
One of them is it?
If it is degenerate eigenvectors.
Degenerate, yes.
So that is the case where it will it can happen. It is not that it will always happen, but it can happen. But it can always be, you can take linear combinations and you can always select them in such a way that they are simultaneous eigenvectors for both of them. I have a ready-made explicit example of that. 4x4 matrix. Very simple. You can construct one thing and you can see that they are not simultaneous eigenvectors. Then you can take linear combinations and they will be simultaneous eigenvectors.
for an example, the three-particle Hamiltonian at
Okay.
T.
No, from quantum mechanics you can take one example. Yeah, like what is your example?
Three-particle Hamiltonian
Okay.
with the momentum operator. But,
Yeah, that's a good example. Let me mention for everyone. That's a good example. I did not occur to me. What is the free particle Hamiltonian? P square by 2 in 3 dimensions. and if I take momentum operators, they commute. So I have solutions K dot R. These are eigenvectors of Hamiltonian as well as momentum. Okay. Now if I take P square by 2n and take angular momentum operator L square and Lz, take any two, they commute. This and this commute, this and this commute, this and this. These also have simultaneous eigenvectors. Okay. So these eigenvectors are some JL spherical Bessel function and YL theta phi. Now what is your statement? I want to stick to your question and your statement. So I take P particle and then do what?
I'm asking that whether suppose VT4 I one dimension.
No, 3 dimension is important. Let me answer you and then you tell me whether I have understood your question correctly. Suppose I construct 3 particle. So let us first keep this in mind. 1 and 2. There are 2 situations. I start with Hamiltonian. Hamiltonian commutes with P. I also know that this is simultaneous eigenvector. So, but supposing I started to find the eigenvectors in R theta phi. I start with Hamiltonian. I try to find. I find it simpler for my reasons to solve in R theta phi. I will end up with this. These are not eigenvectors of P, although P and H commute. But I can take linear combinations of this and get this, which are simultaneous eigenvectors. Forget this. This is not very important for this discussion. Same thing can be repeated here. If I start solving P in R theta phi, P particle Hamiltonian, I will end up with simultaneous eigenvectors of L square and Lz. But if I start solving in Cartesian coordinates, I will end up with this. But this is not an eigenvector of L square and Lz. I can take linear combinations of LS and get eigenvectors here. So I suppose it answers what you are saying.
It says that everything is
in general, you will require taking linear combinations.
so that part is experience, that how to, what kind of
That you have to work. There is no general answers. You have to work case by case, I think. There is no general answer. General answers can be formed, but basically, yeah, I cannot give a general answer right now. So here you have 2 examples. This example, Hamiltonian and P commute. This is simultaneous eigenvector, this is not. One example. Second example, Hamiltonian L square and Lz commute. And this is not this is eigenvector of Hamiltonian, but not of this. So if I just find eigenvectors of one of them, it will not be eigenvector of the other one which commutes with this.
in one dimension there is an interesting problem.
So one dimension also I will give you example. First let us get your question.
For IKX type of waveform, evidence of this H as well as P. But if you go for the combination, say sine or cos. and
Yes,
answer negative
correct.
function.
You have put it right there. Yeah. Let me write that. One dimension. Yeah, that's also that is a very good example because it is not simpler. You have Hamiltonian one dimension and momentum operator. The operator is 0. So what is the Hamiltonian? Hamiltonian is minus h cos square by 2 d square by dx square and psi plus lambda psi. This is equal to k square psi. So we have this. So we have to solve this. This is the eigenvalue equation for Hamiltonian. Suppose we solve this and we get this solution P power ikx, P power minus ikx. We get these 2 solutions. Then we ask whether these are eigenvectors of momentum. The answer is yes. Somebody else will say, no, I will write the solution as sin kx and cos kx. These are eigenvectors of the Hamiltonian order, but they are not eigenvectors of P. So we have to take linear combinations to do this. The same process will apply in general, and in general you can always find simultaneous eigenvectors. That's a theorem in vector spaces. Yeah, this is a very good example. Very clear that if I find the eigenvectors of one of them, the other one may have eigenvectors or may not have eigenvectors. How long will you continue?
Sir, T is ready now.
No, time telling. T is ready or not is the second ready.
It's time.
So let me just take 2 more minutes and we'll stop. So for third postulate will take time. I'll just mention 2 important points of third postulate. There will be more which will follow. That is following. Suppose I have an operator x. You can think of anything. P or Hamiltonian or anything. Then you make a measurement. This is postulate, I call it postulate. You make a measurement of corresponding quantity x. Outcome of experiment will be only eigenvectors. Will be one of the eigenvalues. Nothing else. This is one statement. Second statement is okay. So if lambda 1, lambda 2, these are eigenvalues, you will get these values with different probabilities. This is the general situation. If you measure this particular quantity experimentally, you will get one of the eigenvalues with lambda 1, probability p lambda 1, second eigenvalue, etc. There are special cases which are very important. Special cases when one result is one probability is 1, all others are 0. So you always get lambda k or lambda 1. That is a special case of this. And corresponding eigenvector is what gets the state of the system value. Okay. So I will write this and stop this part. Next is how to calculate probability. We will see. So let me complete this part. So if x gives eigenvalue lambda with probability 1, all the probabilities are 0, probability 1, then we know the state corresponds to the eigenvector. It was for the eigenvector x. So it will be some eigenvector, that eigenvector will represent the state of the system. Okay, this is incomplete, but this is a very important part. We need this part for our discussion. The other part is how to calculate these probabilities. So we are now getting closer to experiments. If we know experimentally something, we are able to say some information about the state of the system. So far, we did that. I think this is the right time to stop.
Ashok, last comment you can make. This measurement, this thing, von Neumann measurement.
Sorry?
This is the von Neumann measurement.
Okay, I will accept whatever you think is.
No. What I am saying is, this has been generalized
in the-
which Sridhar will be talking about.
No, I sort of keep away all those
Yeah,
questions.
this is the one which we normally use all the time.
Yes, this is the one which we normally use, that is right. Yes. These states are very special and they are very
Please
important.
ask it.
If I know definitely spin is up, that state is very important. If I know definitely that spin is down, that is very important. But if I know spin is along some other angle alpha, right, then the difference. Then we have to work. So these are special states that shown in instruments. That if I know probability of getting lambda is 1, all other probabilities are 0, then I know the corresponding state, which is the ideal vector of that. We'll see examples of this later when we start doing spins.
So please arrange outside. So please have it and please be on the scene at 3:10 out of 15 minutes.
R. There are only two possibilities. So when I write matrix I will write like this. Okay. I will put a wiggle below. This means a matrix. This hat means operator. So I can write this matrix as, start with matrix element of half Fx half, then half. You have to calculate this matrix element. In Dirac notation, this is all that you have to do. Then half, this will be half Fx minus half, and this will be minus half Fx and minus half. So we have to calculate this. Okay. If I have spin 1, this matrix will become 3 by 3 because the Sx will have more values 1, 0, minus 1. Anyway, let us not worry about 1 or higher spin. Let us concentrate on this. So how do we calculate? The rules are given there, except as I said, so S value is half, M value is half. So you just put it here. You just press S is half, M is half. So just like this will be minus sign for minus sign. So if you distribute the half, this becomes 0. So S plus actual half is 0. And this is easy to understand why this is becoming 0. Because spin projection cannot increase. Basic operator increases spin projection by 1 unit. So on anything it will try to make it 10 plus 1. But 10 plus 1 for half to CYB is not possible because we have spin half. So you can see that this should become 0 and that formula gives you 0. What about this? You calculate and then this gives you 0. So I want S plus 1. So this S plus 1, this will give you half. S plus 1 minus half will give you plus 1. It increases the M value by 1 unit. So now let us come to we have these things. I want this. So I close this. I know the answer. Actually, I am now going for S plus. Let me put S plus. We have come to S of x. Yes, one more bit. We want S plus matrix first. Yeah. Question. Sorry. Zero means null vector. Not null cat. There is nothing like null cat. Null cat has this Professor Mani has pointed out. Null cat, when we write cat and 0, that has a special meaning that we will have to tell. When we write 0, 0 operator, 0 number, 0 cat vector,
both cases, right?
You have
So
to have
therefore, they are
complex number
polynomial.
0,
Now let me calculate
operator 0,
P inverse
vector
also
0,
here.
we
Once அதை கண்டுபிடிச்சிட்டா நம்மளுக்கு
use common symbol, you will never go wrong. Don't worry.
Cleared
Then
the
what?
CSS
Some
particularly
mathematician
under
has
the
said
History
it is
question.
very clearly.
Okay, so
We will use same symbol. I think it is almost. It's a jet vector, yes. It is an L vector, yes. But we don't use a different symbol. You are right. I am not contesting. I am not saying that you are wrong. It's a jet vector. But we don't have to worry about this whether it is a jet vector or what. Because product of 0 and L vector, 0 operator will always give you 0. Alright. So we want this one, s plus half. So I just close this. S plus half, I have to take scalar product with the half. So scalar product of this thing will half and minus half will give you 0. I take scalar product of this line with half. That will give 0. If I take scalar product with minus half, that will also give me 0. Because it is not 0 is 0. You multiply 0 with anything that is 0. Minus half. Okay. Okay. Sorry. No, I am taking this one, multiplying with minus half. I am taking only this one. And now I will take this one. So this gives me the first row. First row, first column. You need a first column. Something is not right. S plus I should get 1 here. Okay, so that is half half and half minus half half. Something is not right here. Yeah.
Minus a half and plus 1.
This is not right. This should be minus half. This is low index, half minus half. This is column from this. Now it is okay. So this column is 0. Now I calculate this column. So same thing. I have this part and this part, which is that equation. So I just multiply by half and minus half and get my answer. So when I multiply by half with this, I get half half. That is normalization of vector half. So that is 1. So I take now this equation and multiply by half. So right hand side is just norm of this and norm, everything should be normalized. So this is 1. When I take the second 23 minus half with s plus and minus half. So what do I get? I have minus half here. And this part is on here. These are different eigenvalues. So they are not orthogonal. So I get here. Different eigenvalues, the scalar product is 0. For a Hermitian operator. So that gives me the second row. So it gives me 1, 0. So I now have the matrix S plus. This Dirac rule is, this rule for constructing matrix in Dirac notation is very easy. So we have constructed this matrix S plus for its spin half 0, 1, 0, 0 multiplied by x cross by 2. That x cross by 2 is always there. I may miss somewhere. It should be there in this side. X cross. Remember there is a x cross. What is S minus? You can repeat this process for S minus. I will simply say S minus is Hermitian adjoint of this and take the Hermitian adjoint of this and write this x cross 0. You can repeat this process without any problem. S Z. understand these things if you remember your process. So I write down the matrix. Let me write how the description is, then I will write the matrix. The description is this. This is what we want. So always we can back when I multiply by half, I get half x cross. Sorry, this is x cross is not there. It will come here. We get half here. When I multiply by minus half vector, this is a orthogonal to plus half. So we get 0 here. Similarly, the second line. We get 0 here and half here. So there is a final answer for all the three matrices. And I bet when you make your work, you can also do this for English. You can do over 1 divided by 2 in this. Yeah, this should be minus. Yeah, because the eigenvalue is minus. So final answer is we have now constructed these operators and we can use the matrices and their properties to do our calculations. Then we don't have to look at combination ratios. So I will summarize the results by saying that these are H cross by the sigma, where sigma are Pauli matrices. These are so sigma x is 0, 1, 1, 0. Sigma y is 0, 5, minus I and 0. And sigma z is 1, 0, 0. I have left something here. I have s plus s minus. I can add and subtract with sx and sy. So if you add and subtract, you will get sx and sy. Then you can see this. So any questions on this? Most books will give you the answer directly. They will say they satisfy the computational relation. They will not go through this process. I am going through this process so that you can see the logical connections, how the actual construction can be done in any situation. It doesn't matter if it is half or 2 or 1. This is important mostly for atomic physics and or quantum physics. Everywhere it will become important. So we have actually completed first part of our description of spin half, which corresponds to the particle. We have found a way of representing the particles by matrices. And we have worked out one example of spin half matrices. Okay. Now let us see what is the second part. Second part is the states of this particle. This concerns only spin operators, observables and so on. So states. So I will erase this. So what is that we have done? By the way, when you are doing this, there is some amount of vector spaces that I have not, since we are not discussing vector spaces, let me mention that also here. We have represented operators, spin operators, by And giving the answer, there are definite rules which tells you that this is the answer. Okay? Because we have taken this as the basis will always be represented in this particular form. Okay? The first row is half, first column is half, so 1 will come in the first element. So these are normalized values. So this is, we have vectors 1, 0, this vector is up means the child is maximum value is half, and this reference is down. This means n equal to half and n equal to minus half. So we can say these vectors represent the states of the particle. It is along z axis, this is opposite to the z axis. And what is the whole vector space? The whole vector space is, if I can say so, the whole vector space consists of all linear combinations of the basis. This is the basis of all linear combinations. So if I take one linear combination, what am I going to do? So let me give some name. Some pi 1, pi 2. I will call it pi plus and pi minus, or 1 minus 1. 1 and minus 1. So I will take the general vector in this vector space will be linear combination of these two, where alpha beta are complex numbers. So if I put these column vectors, for all pi 1 I put this, for pi 2 I put this, I get alpha beta. So this is the general vector in the vector space of spin half. In the state space of spin half particle. What it means is, if I am looking at only spins, and if the particle has a spin half, it is completely described by a vector like this, a two-component column vector, and because it has to be normalized, alpha square, naught square, beta square, naught square. So every vector will represent spin in some way, or spin half particle. Every state of the system, whatever way it is spin is, it will be represented by these two numbers. So we have a complete description of the states as well as of the particles in terms of the language which we understand very easily, column vectors, etc. Now if I will sit down, you think, ask questions. You think, suppose you have to do the same thing but spin. One, how will you do? Or what will be the results like? Start thinking. This is already known, well known. You probably already know this. Now you start thinking. Suppose you have to describe spin, but how will you describe? So first ask, what are the allowed values of S Z? Answers. Allowed values of S Z for spin 1. I have given all the answers. Anyway, let me concentrate on this. We'll come to this exercise after. About this, any questions? Because there is something more to that in this direction, so let me not deviate too much. We will come back to spin 1 keyword for anything you want. But let us complete this for you. So this is what we have. If you have any questions, please ask. I want to stop 5 minutes. Because now we have to see how we are going to interpret, how we are going to calculate, probability, and so on, what are different things we can do with this spin half. Let us understand this system completely. Understand means how it works, how we calculate different things. This will be upgrading your technical skills. Nothing more is required than what has been done here. And the cost is. No. Just cut it or it will stop. I will not take the call. Okay? Okay, check out this one. Very good. That's all. It isn't more than that. Actually, very little physics has come to talk. Now we have to start asking physics questions. One physics question is what are the eigenvalues of S phi? What all allowed values of, suppose I make a measurement of, right now we have focused on only S Z. That is the standard thing. Suppose somebody says I am going to measure S X. What values are you going to measure? Take S X, find its eigenvalues. Somebody says I want to measure S Y. Take S Y matrix, find its eigenvalues. Somebody says no, I measure in some other direction, 1, 1, 1. Take the spin along that direction, construct the corresponding operators, find the eigenvalues of that. So you have to now keep on applying the postulate. Postulates tell you the eigenvalues are the only thing which will come. Somebody says I am measuring the spin in direction 1, 1, 0. So take that component of spin, find its eigenvalue. That is it. Somebody says I know my spin and the spin of my electron is in this direction. But I want to measure the spin in this direction. What is the probability that I will get half or minus half? Again use postulates. This is the kind of question that will be asked. That will be a very good exercise. That is what he is suggesting. So you have to write this matrix acting on a two component column, alpha beta equal to some lambda alpha beta. So you have to write this whole thing as a two-way matrix. Then you have to write this matrix acting on alpha beta equal to some eigenvalue lambda alpha beta. Calculate alpha beta. You will find lambda can have only two values plus minus alpha along any direction. So there will be more such things coming. I think we will try to stop here. We can start unless they give improvements and they have improvements. No, there are many things I have, but please.
Suppose you make the operator A squared is 1. What are the
Okay. Okay, these are little tricks that one has to know. Yes. So I will go this question. First, you have anything to say about it? Anyone about what has been said? First question. We will now have a volley of questions coming from both of us. I have a question back on all kinds of problems, all areas, on my laptop. Some of that has gone to viewers, but it's not everything. So, is there any problem with this? Do you see any problem? Or you understand what is the answer? If there is any difficulty, please ask. Yes. Sorry? Which problem? No, that properties of polymatrices we will discuss separately. If you see in my website, you will see listed there some 12 properties. So we can discuss all those properties if necessary. I have not planned, but any questions like this we can discuss. So what is the question determinant of? No, why it is minus 1? Okay, it is minus 1. So, but in what context is it? So you can calculate and see what you have to do, right? Determinant of sigma x calculate, determinant of sigma y calculate. Why do you want to do? No, my question is starting from what do you want to do?
Suppose I want to start from the combination relation of sigma x.
From combination relations you cannot do. I will tell you what you can do and what you cannot do. Let me keep that aside. There are certain relations which you can write from combination relations. There will be certain other relations which you cannot write. So what we are asking?
If I start with the combination relation,
Okay, I will try to give a tentative answer.
what fallacy I will take?
Spin operators, what are their eigenvalues? In this case, half and minus half. If I take determinant of spin operator, that will be 1 minus 1 by 4. Product of all eigenvalues is the determinant. So spin half case, the determinant of spin operators will be minus 1 by 4. H cross square. So sigma matrices are, you know, now the determinant of sigma matrix will be minus 1. I will follow. There are general statements which can be made about every spin. There are statements which are specific to spin. So let me just answer your question, then stop. compare this and this, you get what we are asking from what we have done. Otherwise, you can write directly and calculate. But it also tells you how things will change if I have 3 by 3 more than 4 matrix. If I have spin 1, I will have 3 by 3 matrix. This will become cube. This will become 1, 0, minus 1. So the determinant will become 0. So that will become 0. 3 by 2. Now you can calculate for anything what will happen. So this method tells you some extra things, what you can do for any spin, but you know where to change. If I have 2 by 2 matrix, if I have constant sitting here, I will get 2 powers. If I have 2 by 3 matrix, I get determinant, I will get 3 powers. So this is one case it will change. Product of eigenvalues will change. Rest of it will remain common and will remain same. Does that answer your question?
I wanted to start from another point.
From?
Suppose if I write the commutator relation, this I know, but if I start with the commutator relation, then there is a problem.
No. The point is, you want to fix your starting point as well as end point. There may not be any solution. No, we'll discuss this. It may be possible, it may not be possible, I don't know. We'll discuss this.
Suppose if I want to do the same thing for the trace, then trace becomes 0.
What do you mean the same thing for states? I don't understand.
If I start with the commutator relation, and if I calculate the, suppose the sigma x sigma y commutator, sorry, x got sigma z, and if I take the trace on both sides, then the sigma as the trace of the commutator is always 0. So this becomes the
Yeah, correct.
this becomes 0.
So certain properties you can derive from combination relation, but I am not sure whether everything can be derived. That is not
If
clear.
I start with for the determinant of the commutator is also 0.
No. Determinant of combinator, why should it be 0?
Because AB is
Determinant of any two matrices, if I take combinator of A, B, why should it be 0? Base is 0.
determinant is not 0.
If I take two matrices A and B, and I take combinator AB minus BA, determinant will not be 0.
What is the determinant of AB minus B?
Trace is 0, but not determinant.
Determinant of AB minus BA is not determinant of AB minus determinant BA.
Okay, we'll stop here. Continue discussion between discussion. I have problem. Okay, thank you. So now, tomorrow please come prepared with problems. I will post some problems and send you WhatsApp message. Already one problem set. What I suggest is, maybe I will put it on WhatsApp. What you should read before we start solving. Okay. So I will put a message on WhatsApp, you see that. This we will call space wave function, and when we come to other places like hydrogen atom, we need to put everything together, spin and space both. We will see why. So, but we will not take any situation like this, but this is possible. This is the most general thing that can happen. I wish we had more time to elaborate on this, but some of it will come, more details will be needed when I come to helium atom and so on. Okay. Now that is more complicated, but right now I want to discuss examples and problems, and as I said last time, we will discuss examples and problems in the first session. Now for small problems you should not spend doing too much of time, that is my idea. Something which can be understood just by thinking, you need not do 2-page calculation. If you can figure out how you will do, and if you are confident, proceed. I am not very particular that you should show me full answers. But you should be confident that you know, and you should be able to figure out how this has to be done. So I have listed some short examples with that in mind. Okay. These things I will explain how it is to be done, but I want you to think. And these are all very similar problems. There is nothing not, these are all very simple problems, and so let us look at, these are all similar and very simple problems, but you must understand them, and the understanding of these things will now require use of postulates. So just read only one. I have too many things here. Just read 1A. I will read the allowed values of each of these three spin operators Sx, Sy, Z are plus minus h cross by 2. If I take Sz, we know from theory of angular momentum that allowed values of Sz is for spin half plus minus half. I will, h cross takes care of units. Okay. But same thing applies to Sx, same thing applies to Sy. And it applies for any spin, not just spin half. Whatever we have said about spin Sz, it applies to other components. So I want to discuss this, because what I have written here, it is not obvious. The full discussion is not there. So I will just take the first statement 1A and discuss this a little bit. And if you have any questions, you can ask. Then we will go to the next example, like that. So I will give you details. They are not written here. I will give you details, and for that you don't need to do anything. You must understand how it is to be done, how it comes from postulates or from where we will understand this. So Sz we have seen, it comes from angular momentum algebra. Now I want to check that Sx for spin half has eigenvalues plus minus by half h cross. I will leave h cross now onwards. So plus minus half. These are the allowed values. What should I do? You just imagine what we have done in this class, in these lectures, last lecture, this lecture, previous lectures. See, we know the spin operators, right? We can construct, in principle, you know how to construct the spin operators for any spin. So spin half operators, I have actually given you the matrices. So I want eigenvalues, I can sit down and calculate eigenvalues, eigenvectors. Is there a problem? Should I calculate? If you want me to calculate, I will calculate. I want you to look at only statement number 1A. 1A says Sx, Sy, Sz, all of them for spin half have eigenvalues plus minus half. So you have the matrices for spins. So calculate eigenvalues. I am assuming you can calculate, all of you have done enough algebra to calculate eigenvalues. So you write Sx matrix, calculate eigenvalues, calculate eigenvectors, then you will see eigenvalues come out to be plus minus half. Similarly, you can calculate for Sy. What I have not written will come later. Take any component of spin along any direction, it will have value plus minus half. That maybe I will calculate. Or let me just do it, because there are other things. Let us read this part 1b. 1b says that for spin half particle, the spin wave functions corresponding to z are this. Sz are 1, 0 and 0, 1. H cross by 2 is the eigenvalue, corresponding eigenvector is 1, 0, and this is 0, 1. This we have discussed yesterday. One way of doing it is write Sz. Sz is sigma z, 1, 0, 0, 1. I should add little explanations, because for some of you it may be obvious, for some others it may not be obvious. So please bear with me. If you already know, it is obvious to you, because for everyone it may not be obvious. So I will give some hints. What is the Sz matrix? Sz is That is, you should also think, you should not try to calculate every time everything. You should look at the expression and try to see whether you understand the answer. Okay? So, Sz, if I leave out h cross by factors, that takes care of unit. Sz is half, half, minus half and 0. It is a diagonal matrix. If the matrix is diagonal, we know the eigenvalues. Diagonal elements are the eigenvalues. So, the eigenvalues are half and minus half. We also know the eigenvectors. The eigenvector for half is 1, 0. The eigenvector for minus half is 0, 1. I don't need any calculation to do, but if you are not sure, then please do the calculation, get this answer. I am only saying by looking at it, you can decide what is going to be the eigenvalues and what are going to be the eigenvectors. That is my next statement here. Okay? Is this all right? Anyone? Anyone has any difficulty? Do you think a calculation is needed? Similarly, if I have 3 by 3 matrix, if I go to spin 1, suppose instead of spin half, we are talking about spin 1. Then Sz will have values. 1 means, you remember, S minus S2 plus S. So, plus S is 1, minus S is minus 1 in the steps of 1. So, Sz has 3 values, minus 1 and this. So, if you construct the matrices, you will get 1, 0, minus 1. So, these are the eigenvalues which we have gotten from angular momentum algebra. In the matrix representation, these are the eigenvalues. What are the corresponding eigenvectors? 1, 0, 0. If matrix is diagonal, then life is simple. You can just say the first one eigenvector is this, second eigenvalue, this is the eigenvector. Don't have to calculate. If you calculate, you will get this. And third one, the eigenvector is this. All this can be done if the matrix is diagonal. There is no need for any calculation. Now let us come to 1c. 1c, we will do the calculation. But let us first understand the statement. For a spin half particle, spin wave functions corresponding to the values h cross by 2 plus minus half are, this is the plus h cross by 2, this is the spin wave function, normalized spin wave function. For minus half, this is the normalized spin wave function. If I have to get this answer, what should I do? No, I am saying if it is diagonal matrix, don't do any calculation. Look at it and write the answer. If it is diagonal.
1, 0, 0 is trivial. 0, 0, 1 is also trivial. 0, 0, minus 1 is trivial. But 1, 0, 1, 0 is not trivial.
No, just why do you say it is not trivial? No. In this case, if the matrix element, if the matrix is diagonal, you can always write this. It may sound non-trivial, but that is the rule. If you want, you can check by calculation. I want to calculate.
Sir, I understand
Huh.
what you mean. You mean that the columns represent the eigenvector.
Columns represent eigenvectors 1, 0, 0, 0, 1, 0, 0, 0, 1.
But if your eigenvalue is 0, whether it should be 1 or not, that comes from normalization.
No, I am always taking everything to be normalized. Let us have that understanding. I am always normalizing, and it is not always necessary, but it is better to keep it normalized in these simple cases. What you are saying is right. That way, even 1, 0 is not normalized. You can put an arbitrary constant there. You can write alpha 0 or 0 beta. So, even others are not, will not have entry 1. So, if I keep normalized, then what I have given is the right answer. Even then there is a sign, you can put e power I delta. Okay. So, I want to check what are the eigenvectors of Sx. The answer is given to you. If you are sure, tell me, I will skip this calculation. If everyone says, no, let me put it this way. One person says, do the calculation, I will do the calculation. Anyone wants me to do the calculation, I will do it. One person. Please feel free, because this is your business. You have to ask. Yes. No, I am coming to physical significance. See, my approach is very simple. I do the mathematics and physics separately. Once I understand mathematics, then I will come to physical interpretation. Let us do our mathematics right. Then we can talk about physical interpretation after that. So, I will come to a physical interpretation of all this. That will come through using the postulates, especially number 3. No, you probably want to understand why are you doing this problem, right? I'll come to that. No, right now I am only saying I have problem in which I know the matrices. Can I calculate eigenvalues? Can I calculate eigenvectors? Now it so happens these matrices are coming from spin, so I bring in spin. But whatever you have in mind, please keep your questions. I will come to every question that you may want to ask. So right now I am only discussing mathematics of spin half formalism. Okay? Mathematics is independent of how you interpret. And to interpret, I must get back to postulates. So we will do that one slowly, one step by step. Don't want to jump steps. Okay? If I am sure that all of you can do this mathematics, I will skip and then I will go directly to interpretation. So right now the question is, we have obtained the matrices for Sx, Sy, Sz. I want to know what are the eigenvalues and eigenvectors. So Sz is diagonal, so there is no problem. Sx for 2 by 2 is very simple form. You can work out. You want to work out? Take your time and work out on your paper. I will come and see. You know, you have to tell me what should I do. You want to work out, or you want me to work out on board, or you want me to skip. You have 3 options. You don't have option to keep silent. No, everything is fine. If you want to work out for yourself, please do it yourself. I will come round and check and help if necessary. This is my concept of tutorial session. If you are confident, we need not waste time on this. But if one person says, I need help, please work out on board, I will do it on the board. I think what I suggest is, if you are confident, fine. But if you are not sure, you want my help, you start working it out, I will come and see. Write Sx, Sx is what? 0, 1, 1, 0 and half outside. Please start calculating if you are not sure. If you are sure, you don't have to. That is up, you have to decide about your confidence level. You learn only by doing. You don't learn anything by listening to a lecture. At some stage, you have to start working out, calculating, and so on, and start thinking yourself what has been done. So, are you sure? Shall I assume you are sure? Then you please work out, write Sx. You have the expression for Sx, I will write half, 1, 0, 0, 1, 1, 0. Or 0, half, put half inside, remove from outside. And half, 0. And calculate eigenvectors and eigenvalues. I am removing H cross factor. H cross will come and multiply. How about you? Can you calculate? Are you sure? How about you? Have you understood the problem I want you to do? The problem is, I think you missed some part of the lecture last time, is it? So the problem is we have derived spin operators for spin half. So Sx, Sy, Sz. These are some matrices. That matrices I have given in class, in my lecture notes, you can see on the internet. I have given last time. If you have missed that, I will give again. All these lecture notes are there on internet. Okay. So the problem is there is a matrix spin half. I have written Sz, that is diagonal. I want its eigenvectors, eigenvalues. Then there is a matrix Sx, x component of spin. I will give you the matrix. Please find the eigenvalues and eigenvectors. It's a 2 by 2 matrix. You can do it very fast. So please write and pass it on to others. Sx matrix, write Sx equal to S, x component of S. X component, how do you write? No, how do you write x component of S? I will write the whole thing. I have a matrix. It is like vector having x component. It has 3 components. Sx has, please pass it on. Find the eigenvalues and eigenvectors. Yeah. So, how about you? I will come to everyone. Yeah. You can start with this or half. Eigenvectors will same, but eigenvalues will change. So, yeah. Yeah, so sigma x. So, yeah, please. You can calculate. If you are confident, you need not calculate. If you are not sure, then you verify. The answer is given there.
But relation is correct, right?
Sorry?
What I said is correct.
Yes, correct. Yeah, but I don't want to. I want to keep things simple. You can do that way also. So let me write some basic equations. I will spend some time. Then I will actually do the calculation here. I want to go around and see and help you understand the problem. So what I want is, last time we have derived this. Sx is equal to, I will remove h cross factor. I assume work in units such that h cross is 1. So 0, half, 0. This is Sx matrix. Please start finding eigenvalues and eigenvectors. Sy was 0 minus I by 2, 0. And Sz I have already seen, half, 0, 0, minus half. So I want you to take this and verify that you are getting this answer. If you can do this, then this answer you can also do. Same way with Sy. So please spend 5 minutes, you should, on this. If you have done this exercise, you need not spend any more time, effort. See, once you are sure of mathematics that you can find eigenvalues, eigenvectors, you can go and start discussing physics without worrying about how to do mathematics. Or there is another option. Maybe one of you can come to the board and work out for everyone. Can you do? Or somebody else? Okay. This part of the board. You don't have the full board, you have to write a little, press hard so that it is visible to everyone. So I will work it out for you, but you should continue doing on your notebooks. I will come and see. So where do you start? When you have to find eigenvalues, what is the first equation that you will write? Yeah. And solid is a magnetic material. Okay. So there is some magnetic field inside. And I suppose you don't care how the magnetic field is produced. Let us assume that there is a magnetic field. It has certain properties which we may use afterwards. But how do I set up a problem of a neutron coming in and getting diffracted? So I have to look at neutron. Now neutron is a neutral particle, but it carries magnetic moment, spin and magnetic moment. Even if generally it is expected that a neutral particle will not have magnetic moment, but it is not an elementary particle. It consists of quarks, let us say, moving inside it, and they give rise to some magnetic moment. So neutron is a very nice particle that it gets affected only by magnetic field. It will not see any effect of electric field. So if I have magnetic field, it will be changing from place to place. So this B which I have written will depend on x, and S will become the neutron spin, and rest is the same, Hamiltonian will be same. Then we have to see how incoming, because now things are more complicated. The magnetic field is changing from one place to another. So you have to see if I have an incoming neutron, how it gets diffracted. So spin part description is same. It is same because again the magnetic moment that a neutron has will be proportional to spin by dimensional argument. I don't have anything else which can become magnetic moment. If I have neutron magnetic moment will be a vector quantity. What are the vectors that are available to me? With correct properties, the spin is the only thing that is available to me. Especially at rest, what is the vector that is available to me? Spin, nothing else. So the magnetic moment by just this kind of argument will be proportional to the spin of neutron, even if it is a neutral particle. So the basic Hamiltonian will be just this, spin will mean spin of the neutron, except that now it is a solid and it is not a uniform magnetic field. So the magnetic field will depend on x. Then you will have to do more work. This simple calculation will not work. You have to take matrix elements of magnetic field in different states. Okay, so calculate certain integrals over x depending on what you finally want to do. Okay, but the basic setup is same. The Hamiltonian will be just similar to this in the simplest situation. Okay, any other question? Now we can discuss physics questions. There is more to it coming, but let us now, we can now discuss physics questions. This is not spin orbit interaction. This is no. I have taken, it can be atom, it can be electron, it can be anything. But when you say spin orbit interaction, what does it mean? It means the electron has certain angular momentum, it has a spin, and there is a coupling between them. That is different.
Suppose that is the case, what happens to the relativistic condition?
That I hope to discuss briefly if I have time. Okay. Corrections you have to calculate using whatever method you have, perturbation theory. You have to first write down the Hamiltonian, derive the form of Hamiltonian. How do you derive the form of Hamiltonian? Form of spin orbit coupling. So previously people used to guess. Now if I have to derive, I have to derive from relativistic equation, take its non-relativistic limit. If I don't want to derive, then I have to give some hand waving and get the answer. Third option is give you the answer and calculate and not worry about how it comes. Okay. So, but spin orbit is different from what I am saying here. Okay. In some sense, you can say the spin of electron is interacting because of its magnetic moment, because the magnetic moment of electron is interacting with the magnetic field produced by orbital motion L. That will be proportional to L, orbital angular momentum. But that requires a long discussion if I have to see what is the effect. That requires a calculation to see actually what is happening. But all these spin discussion will be useful. All right. Now, I will give you another physical situation and I will try to motivate what I want to do next. Okay. I suppose, I assume all of you are familiar with the Stern-Gerlach experiment. I will briefly, I will describe a small diagram and tell you. Next, I want to come to calculation of probabilities. So, I want to explain to you first why I want to calculate probabilities. Okay? Probabilities or average values. So, I will give you a situation where probabilities will be needed. Suppose I have an electron and its spin is along some direction, let us say spin is along Sx, x direction. Okay, I should not write x, along x axis. I can have an experiment and I can measure its spin value along z axis. Okay. So, I can ask what will I get, what answer I will get if spin is measured along z axis or y axis for that matter, or anything. Z is I am taking only for simple case, but it can be any axis, y axis or 1 1 axis or 1 1 1 axis or anything. Suppose we need this information. Where we need this information in actual system, I will give you some idea, some illustration, so that you can keep contact with physics. So, what answers will I get? If I measure spin z or y or x or any direction, I will always get plus minus half, nothing else, because these are the eigenvalues we have seen. That is what the postulates tell me. The answers I will get will be the corresponding eigenvalues. Eigenvalues for spin along any direction are plus minus half. That is what we discussed here. So, whether I measure along z axis or any other axis, I will get sometimes plus half, sometimes I will get minus half. But I am interested in more than this. I am interested in asking what is the probability for plus half and what is the probability for minus half. Okay. Now, I will come and give you an idea where this kind of question is important. It is important in an standard like experiment. But let us first see how we can actually calculate this kind of object. Okay. Classically, there is no spin. No, classically there is no spin. So, I cannot ask this question about spin. No, if you have dipole, it is a different question. It is a question about dipole. It is not a question about electron spin. No, if you suppose what you are saying is, okay, what you are saying is, what is the, let me try to understand. Suppose I have a magnetic dipole, and what do I want to do? If I have a magnetic dipole, it points in a particular direction, that is the end of it. There is no question of asking what happens in some other direction. Classical theory is deterministic. If I know there is a magnetic dipole, it will have certain direction. Suppose if I know the value of magnetic moment, I know everything. But suppose I do not know what direction it is, then I will make some measurements. If I put a magnetic field along some other direction, I will see a cos theta effect. Then I will measure for different directions of magnetic field. Then the values that I will get, theta values will be continuous. Okay. From that data we can find out which direction it is classically.
If I am asking that, suppose the dipole is along x-axis.
Yes, yes.
What will be the component of that dipole?
Classical vector analysis will give you the answer. There is nothing more involved. Vector analysis, no, I have a vector, what is its component along a particular direction? That's all. No, why 0? Cos theta. No, let me, I have a vector, forget spin magnetic moment. I want a component along direction n. The component is v dot n, that's all.
But as per this is perpendicular, no? X is very
No. In this case, if it is perpendicular, it will be 0. Yes.
But still there are some finite values. So that is the
No. What I mean is, in classical case, if you take the component of a vector, it will have continuous values depending on n. Here you take any n, you can get only two values, and same two values. Does not matter whether you are measuring the z component or x component or y component, you will get only two values. You will not get continuous values. Here, if you somehow measure the magnetic moment component along direction n, that will vary as the magnitude times cos theta depending on the direction. If they are perpendicular, the magnetic moment, the component will be 0. So, that is not anything more than the vector algebra. So, you can see the quantization of the component now. Classically, the component, whether it is z component or y component or any component of magnetic moment, is not quantized. Quantum mechanically, the values are quantized. So, we are interested in the following question. I know that the particle has a spin along one direction. I want to measure its component along some other direction. I will always get some values like half and minus half, and I want to calculate probabilities. If I know this, then I can calculate what will happen in a Stern-Gerlach experiment. There the basic question will be reduced to this only. Okay? And then we can understand what is happening in the Stern-Gerlach experiment. Classical theory does not explain the Stern-Gerlach experiment because of this fact, that the deflection should be continuous. Why should I get one beam and one beam? Okay? So, Stern-Gerlach experiment, if you look at it, you have an inhomogeneous magnetic field and you pass electrons. On the screen you get two spots. Let us say if it is a spin half silver atom or something, you get two spots. Here you have magnetic field. Okay. Why are we getting only two spots? The interaction is mu dot b, and that should be continuous on the direction of electron beam magnetic moment. So, I should get continuous spot, but I get only two spots because the interaction is mu dot b. It has only two possible answers in quantum mechanics, plus minus half. So, you get two spots. If you send spin one particles, you will get three spots. But we want to get more information, like we want to say whether this is more intense, whether this is more dark or this is less dark, or we want to compare the intensities, then we need the corresponding probabilities. And that is what I want to explain. How do you calculate these probabilities, which will come in various situations, not just this. This is only one example. Okay. And the other question is, if I know spin is along a particular direction, has a particular value, what is its wave function? So, let us look at this statements. If I know spin wave function is this, then I know that spin is along x axis, positive x axis. X component is plus half, because this is the eigenvector of Sx with value plus half. We have seen in the previous page. So, it is like this, it works both ways. If somebody tells me this is the wave function, spin wave function, what is the direction of spin? The answer is positive x axis. Because it comes from postulates now. Okay. If I know definite value, the wave function or the vector will be corresponding eigenvector. We have discussed what are the eigenvectors of Sx. This is the eigenvector of Sx. If the eigenvector is something else, that means spin has value minus half along the I will give you what all you need to solve problems, what are the tips, some solved examples, some unsolved problems, like that it has been made. So, you can just look at it whenever you have time. I will go to the first problem set which is listed here, problem set for applying postulates to particle with spin. Now, if you have understood whatever we have discussed, you should have no difficulty in solving these problems. This is my claim. If I have explained what, sorry? That you have to ask him. Yeah, I thought it will be helpful if you have printed form, because reading on mobile is not convenient, I understand. So, whatever prints you need, you please ask him. I am showing it because you do not have printed form. If you had printed form, I would have not done this. Okay. Somehow the alignment is not very nice. This is full screen for me, but it is not.
It's okay, sir. Just zoom it out.
Hmm?
You can zoom it out. Yes, yes.
No, I know what is to be done. Something is being cut. No, I know the display has to be. Let me handle this. Let me handle. There is a configuration thing.
There are 2-3 tabs.
Just 1 minute. No, this display, what is the resolution?
It's 1024.
That is the maximum.
Yes, yes.
Oh, then that is why this problem is coming. No, then I will set up resolution of my laptop accordingly. What is the resolution? You have 1024 by
760, 720, 768.
no, you select 768 or there are.
Yeah, that's what.
This seems to be the right thing. Now it will not go out of screen. Is this okay? No, because I set up different resolution for my system. Okay, I think now you can see, but it's not focused properly. It is not focused. No, it is not focused properly.
That's coming out.
Can you read? Okay, I will read out. So, the first question is, find the spin wave function for a particle. It is given that the projection along x-axis is plus half and minus half, two problems. We already solved this problem. Sx, if I say spin projection is half, I have to find the eigenvector of Sx with eigenvalue plus half. Similarly, other one, we have just done this. Next question is, I give you the spin wave function, I do not care where the spin is. I have given you the spin wave function 3 by 5 and 4 by 5, minus 4 by 5. Spin is along some other direction, I do not care. Okay? We can find out the direction also, but I do not care. And please note that it is normalized, the square of first number and second number is 1 if I add up. So, I am always working with normalization, that is an important thing to remember for calculating probabilities. If you are not working with normalized wave functions, then you have to be careful. So, I do not want to get into those problems, I want to normalize first before I start. So, I now give you a wave function and I ask, yeah, yes, that is correct. Any other answer? You can look at it and get the answer. That is what I do not want you to compute unless it is absolutely necessary to compute. You should remember certain critical things which I will keep repeating. 9 by 16. So that is how it started in 98. And just after, then IT things caught up everywhere. There will be triple IT in Allahabad and other places. And that is the time when the Twin Cities students, the number that went down in MSc physics courses. So there was a definite trend. And then when Mendel Commission report was implemented, OBC reservation was implemented, then of course there were lots of students coming from, which was a very different composition of the class. There were lots of students who were first time learners, first time coming to MSc in their family, lots of students from remote villages, and there were lots of, very few students from Twin Cities now. Okay, I think we will start. Yeah, sorry? No, that is because now there are so many things that people want to do, especially Andhra. Most people want to, Andhra, Tamil Nadu included, and other places. Most people go for engineering, especially Andhra. Not Andhra, I cannot say, but Telangana and maybe Andhra also. Most parents and most students want to do BTech and go to US. That is their aim of their life. And parents do amazing things for their children to do coaching in BTech. They leave their job, change the city, settle somewhere else for 3 years, 2 years, so that when they are doing 12th class, and so that they can get best coaching. The parents themselves, they either take leave or basically they settle in a different city where the child can get coaching and try to get into best places in engineering. This I didn't expect. Somebody will change the whole household, shift to some other city temporarily, just for this purpose. Yes. No, the first thing is the person will want to do BTech here. Before that, he has to do coaching when he is in 11th and 12th. So for that purpose, they will change the place of residence, just for that. Huh? Those who?
Those for the rich persons, because
No, even others. I have no. It is expensive, and only those who can afford. But everyone, like I say, physics department, everyone has somebody, some child, some children in the family, relatives family who has gone abroad, settled there. Like we have attenders, 4th class employee, many of them. It is nice in a way, and their children have gone and settled in US. But what is bad is this craze after engineering only and nothing else. That is not very good, because I will tell you a reason. I was part of integrated program when it started in Hyderabad as a head of that integrated program. Then many students will come and say, I did not want to come to science and I wanted to do this and my parents have forced this. Somebody wanted to do economics, he has been forced to do physics by the parents. Somebody wanted to do biology, no, you do mathematics. So there are lots of such instances. So similar thing must be happening for engineering. So that aspect is bad. Otherwise, there is nothing wrong. You want to, whatever way you want to shape your career, it is fine. It should be fine with parents. They should not, I believe, they should not force the children to take a particular thing of their liking. Anyway, so, okay, I think we will start. So, what is that we are doing? We are doing time dependent perturbation theory. So, let me just summarize, because as I keep saying, I have myself found it very difficult subject when I was learning. In the sense, you don't know what is being done. If you understand what is being done, you will probably, at every stage, you should try to keep track of what is being done and why it is being done. Some idea you should have. You should not be lost oh, why this equation is written, how this comes, that should not happen. If that happens, then I think my job is not done properly. So, I would say please ask questions. Okay. So, let me, so my job right now, the way I have planned is most probably I will complete that. Maybe I will have to cut down some details. So, time dependent methods, there are several methods. We are doing only one method, perturbation theory. There are other methods I thought we will be able to do, but there is no time. In the time dependent perturbation theory methods, the perturbation theory, there are three major applications. Okay? And those three major applications require three different formalism. Starting from the same basic equations, there are three different ways of calculating. So, once you understand this and where are those three different formalism applied, then I think you have an overall picture. So, when we do time dependent perturbation theory, starting point is time dependent Schrodinger equation. We have to solve this. This is our starting point. Our aim is to calculate certain probabilities. This is what we want to get at the end, or probability per unit time, whatever the case may be. So, we have to calculate one of those things, and this we know that initial state is some u I or I will write u I, or in Dirac notation it will be I, and final state will be some f. So, the wave function could be f, in Dirac notation it will be written. So, basically we want to calculate transition probability from some initial state to some final state, that is given to us. This is what final aim is, and then we apply to the different processes. Take a particular process, hydrogen atom getting ionized, write the wave functions and calculate. Okay. So, then how do we go about doing it? The method is, first thing I should be able to split. I should be able to solve, exact solutions of H0 should be known. I should be able to solve H0 problem exactly like free particle solution I will need for scattering, which we will do today. So, exact solution of H0, this is not a good notation, I am using U for something else. So, let us just stick to this. So, exact solution of H0 Hamiltonian should be known. What does it mean? It means I should be able to solve this equation and I should know the answers. So, I am using UN for this. So, this should be, so I should know the answers for this, and H0 should be time independent of time. These are the conditions under which on H0. H prime, it should be small in some sense, which can be quantified, I am not doing it, but small in a well defined sense. There is a way in which we can say it is small or large. There are several ways in which one can do. So, in some sense, because you remember that famous episode of Birbal and Akbar. Birbal, Akbar says, I have a line on drawn, make it shorter without touching it. So, the Birbal goes and draws a bigger line. So, saying something is small or big is not, doesn't mean anything unless you say compared to what. But that I am not doing it here. It can be done and it is available. Let us not worry too much about it. Okay. So, this is what we require. Then method consists on, you write h as S0 plus lambda h prime, and at the end we will put lambda equal to 1. And whatever you want to solve, the solution is expanded in powers of lambda. In powers of lambda, and the hope is 1 or 2 terms in powers of lambda are sufficient. That is the hope. It will be an infinite series in general, but we do not have to sit down and calculate too many terms. The hope is if h0 is h prime is small, then we need not calculate second term even, only 1 power of lambda term should be sufficient. And that is exactly what we have done in the last lecture. I have given you the equation, the final answer, which will tell you how to calculate the first order term. Okay. So, the first order transition probability or transition amplitude, I have already done that and I will start from there. If there are any questions on that, let us have it now. First order transition probability from initial to final state, that result has been derived yesterday. That takes some time, I am not going to repeat. I will write the result here and start from here. That. So, please ask questions if you have anything on that. There are 2 things, one is exact equation, and so I will write the basic equations here. Meanwhile, you think if you have any questions, you can ask. So, you solve for the wave function by writing n all n and Cn of t and psi n of x t. What is psi n? Psi n are solutions of time h0 equation. These are solutions of equation with lambda equal to 0, h0 equation. So, this is known. So, unknown object is this. So, we get an equation for Cn. Cn equation is IH cross d by dt of Cn equal to summation over, I had m, so let me write m h prime n e power I omega m n t, and what else, m and something else, yeah, c n of t. This is the equation which is exact. Okay. So, let me not write it, there are too many things already. So, this is an exact equation. I write this because we are afternoon, we are going to start from here. Afternoon, we are going to start from here. Then next thing is expand C in powers of lambda, because C is unknown. Expand C in powers of lambda, everything else is known. So, Cn of t equal to Cn of 0, this is 0 power of lambda plus lambda term, first power of lambda and lambda square, Cn of 2 and so on. So, we can solve equation for Cn0, then equation for Cn1, then for C2 and keep on doing this as long as our problem is not solved. So, as I said, most of the time It is sufficient to solve for Cn, and that solution we have obtained, and that I will write there. I will keep these equations here. So, if this logic is clear, if you have any questions, you please ask. This is how the method will work. This is the requirement on the Hamiltonian. I should be able to split, and the final answer that I need to start from today is following. That is C1, first order transition amplitude. So, CFI 1 means first order at time t is equal to 1 over I h cross integral f h prime, this is the matrix element, initial state, and e to the power I omega f I. Anything else? T dt. Yeah. And given that initial state is some ui and final state I want uf, that is the first order transition amplitude. I am just summarizing what we have done last time. And transition probability will be transition probability for I to f is modulus of this CFI square 1 whole square. This is at time t. So, the transition probability will depend on time. So, this is all that we have done so far, and I want to start from here. As I said, there are three situations where this will be applied. One, I and F, both are discrete energy levels. That energy is not continuous, it is quantized. We had one example, harmonic oscillator, for example. Energy, discrete energy levels, let me make it short. The energy levels are discrete. So, that we have completed. We have also worked out. The second case is, which we will do today. F, that is the state F, the energy of state F, or final state, lies in continuum. An example I have given you, hydrogen atom in the ground state, it is getting ionized because of some interaction. So, the electron is removed. It can move with any momentum. Momentum is continuous, energy is continuous. So, this is different from harmonic oscillator. The initial state has definite energy, final state has definite energy. So, this is initial state. Here the wave function is like u0, hydrogen atom ground state wave function. So, initial state. The final state, electron has certain momentum, so it can be like plane wave. And all energies are allowed, positive energies. So, if the final state is electron is ionized, we have different thing to do, because the energy is continuous. And I have already indicated right in the beginning, in the morning lecture, there are two things which have changed. One is you have to calculate transition probability per unit time, t going to infinity limit, very large time. So, what happens if time is increased? If time is increased, I will just give the answer. This peak keeps on increasing. It will keep on increasing when time becomes larger and larger, because the value is like t square, and this will shrink. It will shrink because the first 0 where it comes? It comes when omega fi is equal to t, omega fi t equal to pi. So, the first 0 will come at omega fi value equal to pi by t. So, this point is here. If I increase t, this point omega fi value will decrease. So, it will come somewhere here. So, if we keep on increasing t, if we look at that expression for larger and larger t, then this peak will go up and the width will shrink. Okay? And we are finally interested in t going to infinity limit, because of that is what we do in experiments. The time when it is detected is much larger than the time of interaction. So, these peaks keep on shifting. So, now once we have understood this, then let us wait for a minute and then we proceed from here. We are actually not interested in this transition probability. We are interested in transition probability per unit time, and we are not interested in transition probability to single state. We are interested in transition probability to a set of final states, which is k and k plus dk. So, we have to look at that quantity and see how it is behaving. Okay. From this, we have to look at that quantity and see how it behaves. So, I will just make some comments. You might ask, if t is very large, this probability will become 1, greater than 1. So, what is happening? The answer is very simple. Your perturbation theory is not applicable. You cannot use perturbation theory for those times. That is it. You must keep higher and higher order terms C2, C3, C4 and forget about applying perturbation theory if time is very large. So, you cannot apply this for very large time. The fact that the probabilities become greater than 1 is an indication that your solution is not valid. Method which you have used is not valid. Okay. But as I said, we are not interested in this quantity itself, we are interested in a set of not one final state, set of final states. So, we have to sum over probabilities for the final states, then we are interested in probability per unit time. So, we have to find probability per unit time. So, let us come to that. That will then we will see the important thing that will come out of it, that quantity which we will call transition rate is independent of time. That is what will be related to cross section. Okay. So, this is the basic thing that we need to start, but this is not the final point that we need for this kind of scattering calculation and many other transitions involving electromagnetic transitions and so on, so many things everywhere. That is why it is a golden rule, that result that we are going to derive. So, we need to do two things now. One is we ask what is the probability for transition to final states. So, the answer is whatever final states you have, you sum over them, and then we need to calculate transition probability per unit time. So, you differentiate with respect to time this answer. So, let us do that. So, what we are interested in, this is our quantity of interest and this is coming from experiments, not from theory. This is what they will measure finally, interested in transition probability for a group of final states. Final states and per unit time, not the transition probability, per unit time. This is what we want to calculate. This is what experimentalists will use. Then you can connect your theory with experiments if you calculate this per unit time. It is lot of things to write. I cannot keep on writing this. So, we will have some notation W. W may look like omega, do not worry about it. So, WFI. This is transition probability per unit time. So, we have to do two things. We have to differentiate so that it becomes per unit time, and we have to sum over all final states. Whatever the final state is, sum the probability over all final states and put that thing here. Remember, this thing is first order result. So, but we are calculating everything in first order. So, we put that probability here, then we are done. So, this is what we want to calculate. Rest is only algebra. And I have given one example. What is the final state? Final state is all momentum between vector k and vector k plus dk in scattering. And what is the final state will depend on the experiment that is being we want to explain. So, it will be different in different experiments. There is no general answer. Somebody says, I will measure, let us say, you have a process. I will just to deviate from here a little bit. I have beta decay process, E nu, proton, electron and antineutrino. Somebody will say, I only want to know how many electrons are coming in a particular direction in a particular energy range. So, he is selecting some other set of final states. So, what comes here in final states is different. So, when we say final states, it is left unexplained because it is different for different experimental setups, different observations, different processes that are measured. Okay. Now, what do we do from here? Then finally, we are not interested in time t. So, we will take limit So, this is what we will do. Now, remember, most of these things can be pulled out. They do not depend on time and so on, but let us keep everything. There is no point in working with a smaller incomplete part of the expression. So, this is, we can also call it transition rate. This is also called as transition rate. Rate at which, rate means per unit time, at which transitions are taking place from initial to final state. But the notation is, this is more or less a standard notation. I will not write this again and again, full explanation, and we start from here. So, I have just copied this here and I will remove this and take limit at t going to infinity. This is what we have to do. This is fairly straightforward and easy. You only have to know certain relations, identities and so on, that is all, nothing more. So, let us differentiate this object because we have d by dt. So, we first differentiate. So, what will we get? 4 by h cross square summation over final states omega Fi does not depend on time. So, I will keep omega Fi square here, but it depends on the final state what you have. So, I am keeping it inside the summation, and then I have sine square, I have to differentiate that. So, what will I get here? I will get 2 sine omega Fi t times, sorry, there was a by 2, I am sorry I missed, this is by 2, because we had exponential omega Fi by 2 and exponential minus sign with omega Fi minus omega Fi by 2. If you go back and see, we pulled out 1/2 power outside. So, inside bracket there was only sine omega Fi t by 2. So, we will get, if we differentiate with respect to time, we will get this cos omega Fi t by 2 into omega Fi t. We are differentiating with respect to time. So, this is the full differentiation of that sine term. So, let us just simplify and see what is happening here, and then the matrix element square will also come here. So, we will write here. This also depends on the final state. So, I cannot pull it out. Now, I only want to first look at time going to infinity limit. Sum over all states we will see afterwards. So, first we look at time going to infinity limit. So, let me simplify and then see what is happening. So, I have 2 here and 2 here, that 2 cancels and something happens. So, this 4 is here, this 2 is here, 8, and this is there, something else should be there. This is all. So, this 2 cancels, but I want to write this as sine omega t cos omega t is sine 2 omega. So, that 2 will cancel, I will write 2 by h cross square, sum over final states, and this will remain, matrix element will remain as it is, nothing, we are not going to touch this. Sorry? No, it is not there. Look at this. This we put so that we can take the limit. We put it by hand at t square here and t square here. I am differentiating this. There is no t square in the denominator. Is that all right? Look at the first expression. There is no t in the denominator. Which term?
Because previously, when you just multiplied with the complex conjugate, then that 4 was not there.
No, 4 comes because let us understand. I will explain. We had e power I omega t minus 1. Then I said we pull out I omega t by 2. We will get e power I omega t by 2 minus e power minus I omega t by 2. Then we are taking modulus square. So, modulus square of this. So, modulus of square of this is 1. This is 2 I sin omega t by 2. So, this 2 becomes 4 there, and we get sin square of omega t by 2. Omega is omega Fi, of course. So, that is how we get 4, that is how we get sin square omega t by 2. So, when we differentiate, we get this. So, I want to simplify. That is what I was going to do. So, simplify means there is 1 omega Fi here, 1 omega Fi square in the denominator, there is 2 there. This 4 cancels, this becomes 2, this matrix element remains as it is, then rest of it I have to write. the denominator. This is omega Fi, this is omega Fi square. So, I have omega Fi 1 power in the denominator. The numerator is I have 2 sin cos. So, that becomes sin 2 theta, sin of omega Fi t, that is all. Now, you check. This is all right. Anyone, any doubts? This is straightforward differentiation and simplification. Now, what do we want to do? We want to take time going to infinity limit. So, I have an expression, and this expression I want to take the limit sin of omega Fi t by omega Fi as t tends to infinity. This limit is Dirac delta function, that you please accept. I cannot prove it now. You can look at books. We can discuss if we have time, but there is no time. I want to do other things. So, please accept there is a formula which tells you that this is 1 over pi delta of omega Fi. The formula is sin omega t by omega limit t going to infinity is delta of omega 1 over pi, or pi over, I am sorry, I think it is pi over pi times omega, delta omega. Let me check. Let me check this. I think it is pi over pi into delta omega. This is a standard formula. I am not going to prove this. This is pi times delta x omega. So, we use this. So, we calculate the limit using this. So, we substitute this. We do one more thing. I do not need anything now. So, I will erase that part. I will get the expression 2 by h cross square. This pi comes from here, limit, and then I have sum over final states. Okay. Modulus f h prime I modulus square, and this becomes pi delta, pi has been pulled out, and delta of omega Fi. This is the transition probability per unit time that we finally want. Now, you see, look at this expression, this is independent of time. Now, we have taken of course limit, but you can go back and check. In any case, that discussion is not very important. This is the final answer that we are interested in, and it is almost the final formula that we need for scattering. We can calculate scattering from here, cross section, which I discussed yesterday, how to calculate cross section. But we will do one more small thing, that is, what is omega Fi? Omega Fi is Ef minus Ei by h cross. So, we will pull out this h cross. If I have delta of some number times x, this is 1 over modulus of delta x. So, using this formula, we will pull out h cross from here. We will write this as, when we see pull out this number, it becomes 1 over that number. So, we will get h cross delta of Ef minus Ei. depend on final state, this can be pulled out, number 1. Number 2, well, maybe even if it cannot be pulled out, I can put EF equal to EI. Second thing is, we write sum over final states, something. So, we have to count how many states are there. So, we have an expression, we want to sum, we will say this is, remember the range of energies in all the cases is small, the cases of interest. If it is not small, we have to revert back to this formula. So, we are counting sum of final states for a small range of energy. Final states can have large range of energy if I measure something else. So, if final states have a small range of energy, I can write this as range of energy times some function, that some function is called density of states. And integral over and summation over final states will mean integral over energy and other variables. So, other variables will give you this, and this formula reduces to what we call Fermi golden rule. So, write this, and now sum over final states, part of it has gone into density of states and part of it will be integral over final energy, but final energy will become equal to initial energy because of delta function. So, what you will get is formula like this, we can write here more clearly. I do not need this part, I need only this part for cross section, but this is the part you will see in most books. WFI equal to 2 pi by H cross, density of a matrix element square times rho of E F, that is all. So, this is the formula which is known as Fermi golden rule. You will have to calculate density of states for the situation you want to explain. So, this formula is Fermi golden rule. You have transitions between different levels of energy because of electromagnetic waves falling on atom, you will use this formula, anything like that. Somebody decaying, I have a nucleus and it emits alpha particles, alpha decay or beta decay or any decay, you will have to use this formula, this is starting point. So, it is called golden rule. In all these cases, you will need transition probability per unit time to a group of final states, because final state is continuous. When a nucleus emits an alpha particle, the energy of alpha particle is not fixed, it has a certain range, or a beta particle, the beta particle energy is not fixed, it has certain range. So, in all such cases, this is the formula which will be used. As far as I am concerned, calculation of scattering cross section, for my purpose I will start from here. I can also start from here, that part will be given in the notes. But right now what I will do is I will start from here, this is simpler for me. You can also start from Fermi golden rule, calculate density of states and get the same answer, which is given in the notes which are uploaded on internet. So, I will do it differently because this is, I find it simpler because of my training as a particle physicist. Okay. So, shall we apply this? How much? Oh, we have enough time. We will apply this and then discuss anything that you may want to discuss. So, all this is not required. So, let me try to write here or copy that formula here and apply to scattering. So, the final formula that I have is W f I equal to 2 pi by h cross summation over final states this is all that we need. If you want to start from Fermi golden rule, please look at my notes on internet. That is more work actually. This is straightforward, what I am going to show you. Now, remember, you have to recall what I said about scattering cross section, how we have to we define scattering cross section. If you remember that, then you can start calculating. It is 3-4 lines. So, I will remind you what I have already told you about the definition of scattering cross section. That has nothing to do with quantum mechanics, classical mechanics, anything. So, the definition is you count. I will write the final answer, probability per unit time of particle getting scattered into the detector. This is what cross section is related to. This probability is proportional to the solid angle of the detector, and it is proportional to the flux of incident beam. Flux of incident beam. Okay. And the proportionality constant is what we call differential cross section. So, left hand side we have the formula here. Flux, let us worry about flux, dispose it off, it is a very simple thing. Then we have to calculate matrix element. What is H prime? So, H prime I will take a potential. So, let us start. Suppose we say that the potential is Yukawa potential, lambda e power minus mu r by r. Why am I taking Yukawa potential? Because when I take mu going to 0, it becomes Coulomb potential. The answer we will get will become Rutherford scattering answer. Okay. That is why I have selected this, because I want to show you how Rutherford scattering answer will come from here. So, I start with the Yukawa potential. At the end, I will put mu equal to 0. So, you will have answers for Yukawa potential, you will have answers for Rutherford scattering. So, this is the potential. Plus minus sign is unimportant, because the cross section is independent of sign, attractive potential or repulsive potential. The differential cross section has the same expression. Only the particle will move away or bent this way, that is all that happens, but the differential cross section is same. So, we take this, then we ask what do I mean by flux? That is one thing. Then we need to calculate the matrix elements, UF, these matrix elements. So, I need the wave functions for initial state and final state. So, if I want to calculate H prime matrix elements, compute this matrix element, I need the wave function of initial and final state. So, initial state, I am saying it has momentum k. So, the wave function will be I k I dot r. This is the plane wave. having momentum k times some normalization. I do not care what the normalization is. Final state, again it is some other momentum, the particles are going into the detector, some normalization and e power I k f dot r. So, these are initial and final wave functions which I have to put in. Now, I need to calculate flux. Flux for incident beam. Now, this is the target and this is the beam. So, the particle can go into the detector if momentum is k or k plus dk. It has to be in this range, dk is this. Okay. This particular direction corresponds to a small solid angle d omega. That is the solid angle d omega we are talking about. That is same as the solid angle of the detector on the target. So, d omega is this solid angle and d cube k, when I want to integrate over all these momentum, then d cube k will be k square dk times integral over all directions of momenta inside this. So, that will be just d omega. So, that d cube k summing over final states can be done by summing over magnitude of momentum and by summing over all directions. And remember, the direction is a small solid angle. Okay. Now, we are through. I can just write one line and stop here. So, you put everything together. Whatever you see on the board, you have to just put everything together correctly and you have the answer for cross section. The cross section is sitting here. Everything else we have discussed how to calculate. So, let me complete the story. Because you see the solid angle is small and we have to integrate over all these directions theta phi. So, we can pull out everything and multiply that function by d omega. That is, I have a function and I have to integrate over a small range of angle, we can just write f times the solid angle. There is no integral to be done. Okay. If I have some function, I integrate over a small range of x, same thing. Suppose I have a function f x and I want to integrate over a small range, let us say a plus delta a to a plus delta x. This is a small range. So, the answer is f x delta x. Because it is small range, we can do this. That is exactly what I am doing for integral d cube k. So, solid angle integral is gone and we get a factor of d omega. We have to only integrate over k. That is what we will do now. So, sum over all final states, I will come here. This sum over all final states will become d omega, so integral one single integral dk k square, and everything else I have to keep. This is only sum over final states. So, let me calculate and let me remove some of those things. Flux we have calculated. So, flux is modulus n square h cross k by m. Okay. This is first answer which I have raised. That is this. Now, the right hand side is, so right hand side of this is simple, equal to sigma This is what we are trying to calculate. Solid angle d omega, this is going to cancel from both sides, and flux n square h cross k by m. So, this is right hand side of this equation. Now, let us look at left hand side. Left hand side has sum over all this, that is the probability per unit time. So, I will remove the right hand side completely and look at left hand side of this equation. Left hand side is coming from the formula that we have derived. Summation over final states. I am applying to scattering now. Okay. So, sum over final state, what did we have? F h prime I 2 pi by h cross. I have the formula there, I have removed anyway. So, modulus square delta of E f minus E I. Anything else? That is all. So, now we have to worry about the sum over final states, and then compare left hand side and right hand side, we get the cross section. So, if this is the initial state, if this is the final state, then we know the matrix element. So, the matrix element is f h prime I equal to initial wave function here, final wave function, complex conjugate and integrate. So, we will get n square integral f final wave function star, the potential you can put here V of r, we have taken this potential, and initial wave function r d cube r, and u f is this plane wave, u I is another plane wave, u I equal to exponent some normalization constant. No, I have already, let us write 2 steps. So, the matrix element is without normalization constant comes here, initial momentum dot r, u f is final momentum dot r in the exponential. So, I have to put these things here, put the potential V r and integrate. So, this in principle is known, everything is known on the right hand side. Now, we are looking at left hand side. So, h prime also I will write here, this is the potential, this is same as we have selected it to solve for Yukawa potential. And sum over final states. So, sum over final states, I can write this as sum over magnitude of final momentum and sum over directions. This is what I have explained just now, d cube k, this is integral k square dk, and this is just multiply by d omega, summing over all direction means multiply by d omega. That is, this is exactly what I have explained here. So, sum over final states is this. So, put the matrix element here, and then we are left with one integral, and we have to do one integral only, nothing else. So, this is the transition probability WFI. So, let us see what is we have 2 pi by h cross. Matrix element we know how to calculate, modulus square, everything is known, we have to do integrals there. Sum over final states I will write this, d omega is just multiplying it because it is a small direction, sum over small directions. Then I have integral over k square dk and a delta function. because we have delta function, doing this integral is very simple. I will do this and that will give you the final cross section. So, allow me 5 more minutes, we started a little late. I will just do the integral, you have to put everything together, you will have the final formula for cross section in the first order approximation we have worked. This is not the full exact formula, because we have calculated transition probability per unit time only in first order. So, this is also same thing as what is known as first Born approximation. You can check that. So, all I have to do is to calculate this. So, how do I handle delta function? Energy is h cross square k square by 2m, right. So, the strategy is I have a delta function in terms of EF. So, I put that here and try to calculate. Initial energy is h cross square, some initial value by 2m, k square by 2m. So, I will put these things here and see what can be done. One moment, let me see, there are different ways, let me see what is the simplest thing. Simplest thing is change the variable from k to energy, that is what you should do. I have to integrate over all k, and I have delta function in energy. So, from k to energy you change the variable, that is what you do. Then you can just use this delta function and write the answer, that is one way. The other way is put this here, use the equations involving delta function and then do integral over k. So, let me change the variable to k, from k to E, f, from k to EF. So, I differentiate, what will I get? DEF equal to h cross square k by m to dk. So, I know dk, why is this 2? No, this 2 is not there, this 2 will cancel. So, I have this formula. So, I get this dk equal to h cross divided by this. So, m over h cross k dE. So, we will substitute this here. So, all this remains as it is, we get integral k square dE into that factor into m by h cross k and delta function in energy, this is EF. So, now I have to integrate over all final energies. So, this tells me that put energy equal to EI, final energy equal to initial energy, that is what the delta function tells me, which means Kf will become equal to Ki, that is all. So, initial and final values of energies are same, initial and final values of absolute values of momentum vectors are same. So, we have the final answer here for this integral. So, let me just write one more line and 2 pi by h cross and d omega. So, I have 2 pi by h cross d omega matrix element square and we have k square, 1 k will cancel, m k by h cross will come. So, into m k by h cross. You have to check the factors carefully and no, I am sorry, it is h cross square. So, this is, I was worried, I have h cross square here. K is 1 power, but h cross has 2 powers. So, I will get h cross square here. So, now I know everything in the left hand side, I know everything in the right hand side. So I get my sigma cross section. That's all. There is nothing more to be done. Do the space integrals, you will get Rutherford formula when mu goes to 0. Okay, I will stop here. If there are any questions, we can discuss. And this formula which you will get from here is the same as Born approximation. I will not. If they come out wrong, then no, we will do it after the lunch. I will write the final formula and then we will check the dimensions. We will do this. Right now it is messy, we have to simplify. Simplify means I have left hand side of my formula and right hand side of my formula. I still have to write cross section in terms of that. Calculate from here. No, this has to be equated to this flux and all that. So then I get cross section, then I can calculate that, check the dimension, I will do that. No, this looks like final result, but this is not the final result. No, that is one exercise we give to students for Born approximation and the scattering cross section. Check the dimensions because it is not very obvious thing. All right, we will stop here. Please ask questions because this completes my discussion of Fermi golden rule and its application to scattering. The way you see in notes will be slightly different, methods will be followed. Especially I avoid calculation of density of states. I just sum over all final states of interest and that gives me the answer. And lot of calculation is hidden inside density of states because you have to ask what is the final states over which you have to sum, then only you can calculate density of states. Okay. So, it is okay, some people use this, some people prefer other one. So, this in principle completes this. If you want, I will calculate the integral, put everything, give you the formula. Calculate that R integral, that takes some effort. But if you calculate put mu equal to 0, you should get Rutherford formula.
Thank you, professors. Thank you, professors.
Okay, today we are completing the first week. So, Professor Manisa, the post director, as well as Professor Ashok Kapoor will be completing the first week in the afternoon sessions. So, those two sessions will be the last sessions in the first week with Professor Manisa and Professor Ashok Kapoor. So, participants will be happy to have the last sessions of the first week with Professor Manisa and Professor Kapoor in the afternoon sessions. So, kindly be available in the hall as soon as you complete your lunch. Thank you. Thank you, Professor. Now it's time for lunch. Yes.
I have one general comment. If you have any difficulty regarding what I have done or anything related to physics you are trying to read and you understand, you can always mention. And my response time under normal circumstances is
Hello.
either you have asked very difficult question.
Hello. Hello.
Material is there on internet. My material is there on internet.
Madam,
Except I have not followed something which I will try to write and put that also. So the approach may be different because those are old notes.
the materials Professor Kapoor posted in the website called Zero Space. So in the website, all the materials are available. You can directly access, ma'am.
Link is available in WhatsApp group. I will send again if you want.
Hello, chicks, hello.
That is one incident I always remember when somebody says, shall I clean the board? All right, I will give you my email address first. Feel free to contact about this course, about any other physics problems, except I cannot answer questions on laser physics, experimental physics, electronics and solid state theory. So, certain areas I cannot do, but most other areas, theoretical physics, quantum mechanics, classical mechanics, statistical mechanics, mathematical physics, I have been at it for now 10 years, putting up material on zero space, but we have reorganized 3 times. Reorganized means complete overhaul, and now this is going on, that process is going on for 3rd time. So, right now material is there, but it is not available, it is not easy for you to find out. So, hopefully this process will be completed in about 3 months from now, because we have new tools, new methods of doing it, organizing and linking things, and it will make things faster for all of you. Right now you just put one keyword search and you will get to the page you want. Earlier that was not happening, you have to click and then click and then click and then you get what you want. So, hopefully this process will be complete in 3 months now. As I said, there is Professor Mani is PhD student Dr. Ranjan Srivastav. He is the system administration and he keeps doing lot of improvements, and I do only the physics part. He does all the background system administration and developing tools for this purpose. So, that site I will write my email address. Please feel free to send email about any difficulty you have about this course or the areas in which I am competent to answer. I will try to answer. My time scale is 48 hours. If you do not hear within 48 hours, you can send me a reminder. That is one thing. But there is a small problem. Many times it happens to everyone. We do not know what to ask. We are reading something, something is not clear, we do not know what to ask. So, my suggestion is, you first you are reading something, take a snap of this with your mobile, clear snap, make sure that it is clear, not distorted, sufficient light, contrast is there, and say that I was reading this is from this book or this journal, and you write whatever you understand or do not understand, whatever you want to ask, whatever way your word is, I will see what I can, how I can clarify, or else I will ask questions. So, this is open to you, all of you, also to all of your students, you can tell this if, but I have absolutely no problem, because this is what I am now doing full time for zero space. And so, if you ask some question, actually it will not be your question, there are many other may be asking, it may help me in rewriting certain things or adding some new material. So, that is why I say, if you have any questions, you are most welcome, because it is not just the question I am answering, it helps me in many a times looking at certain things which I have not seen in a new way. So, remember that it is not that I am doing a favor to you, I am also benefiting from it, and it will be available to everyone on zero space in some form. Only thing is, when you ask questions, make sure that if you are reading some material, make sure to send me a snap of this 1 page, 2 page. Right now all books are available on the internet. Take out 1 or 2 PDF pages and send that to me only. Do not send me the whole book. That will not be very useful. You send out the pages you are reading and say that this is the book, this page I was reading, and this is the difficulty I have. Okay. So, I will give my email address, then I continue with what I have here. This material what I have put on zero space, that link I will send you again, and it is available with Dr. Alexander. That link is there in that WhatsApp group, and it will be updated once I have the access to video recordings of these lectures. Okay. Right now what is there will be slightly different version, but once I have the recordings, I will make it very close to what I have said here in the lectures. So, AKK HCU for Hyderabad Central University. @gmail.com. So, please feel free, I have absolutely no problem because I benefit from your questions. And zero space link for this, for these notes, you go to zerospace.org and search. There is a search box. You search for 22 St. Joseph's College. Search for this, you will land on that page. There will be, it will open in a pop-up window, open in new tab, and you can have everything that I have done here. More than that actually. Okay. Now, let us get back to this and complete this story. I want to make one correction. I have slipped. When you sum over all momenta final states, it is integral du cube k, but there will be a factor depending on the normalization you choose. So, that factor I have missed, and that factor will be, I will write this again. So, I am going to erase most of it, except that this is very important for me. When we sum, suppose we have selected wave function, let us select n. So, we select wave function plane waves a dot r by 2 pi 3 by 2. Then when we integrate sum over all momentum, this is d cube k, that is all. So, if I select my plane wave functions to be like this, so if I select n equal to 1 over 2 pi 3 by 2, then sum over all k is just an integral over all momenta. What I have written is correct only for this normalization, not for any normalization. And if you have some other normalization, you have to modify this. And then you can check all the normalization factors will cancel actually. Okay. So, let us use this normalization and try to get the final answers. So, the final answers are actually here and here. I have to compare these two things. So, I have to compare this final answer with this answer, left hand side and right hand side. So, sigma theta phi is what we are interested in. So, differential cross section sigma theta phi equal to what? This thing. So, d omega will cancel. N I am selecting to be that 1 over 2 pi 3 by 2. D omega will cancel. H cross k by m I will transfer here, n I will transfer here. So, I am not quite happy with this, but let me continue. Yeah, this is fine. So, I will get 1 by n square, I will get m by h cross k from the right hand side. So, right hand side these factors I have transferred, sigma is left, sigma is given by all these factors and this thing. And this matrix element square. This is the final answer for cross section, and for matrix element I should use this as input. So, how does the matrix element look like? F h prime I. So, this is integral over all coordinates wave function for this. So, I have selected that value of n exponential I, final wave function will be k dot r divided by 2 pi 3 by 2. Okay. Complex conjugate of this, h prime is potential e to power minus mu r by r, some constant lambda. Initial wave function is similar thing, e power I initial momentum dot r by 2 pi 3 by 2 and integral over dq bar. So, we have to do this integral. So, let me pull out whatever I can pull out and write this in the form 2 pi cube lambda. So, lambda is gone, 2 pi cube is gone. I will combine these two exponentials and I will define q kf minus ki. So, we will write exponential of q dot r and power minus mu r by r, that is all. What is q? Q vector is kf vector minus ki vector. So, I have to do this integral. Once I have done this integral, I have to substitute in the formula here. This is the formula, square of this has to come here. So, I will write this formula here and we can simplify. N I have selected this, so 1 by n square will become 2 pi cube. Then m by h cross k, something is not right, h cross k by m. I have removed this. Then 2 pi h cross factors, I think they should have same powers, m k by h cross m. You have to check these factors I have erased. So, some factors will come and this matrix element square I should not have erased. Some numbers, factors and matrix element square. My interest is in calculating this matrix element, rest of the things you can do. Yeah, if you can point out where is the mistake, I do not think this factor is correct. This is m by h cross k, this is m k by h cross k, cancels, I do not like that. K factor should not cancel, 1 k should remain. No, I think this is all right. M k cancels, I have m square. Let me simplify, write whatever it is. So 2 pi factors of course will be there. So k will cancel and I have m by h cross power 4. Okay. Let me write whatever I am getting from there, then we will see. M by h cross power 4. Power 4 means 2 pi h cross also I am taking. So, this 2 h cross will go away, h cross power 4 and m square. And a matrix element. Okay. Let us, maybe this is right, I am getting confused. But anyway, all that is a simple thing that can be checked. I want to now calculate this integral. So, matrix element is these factors. This also we can write there lambda by 2 pi cube. So, only this integral is what we have to calculate. I will remove all this. I have written down the wave functions, everything is there. So, this is not needed. So, I have this integral, let me call it some x of k, x of q. Now, it will depend on q and q is the momentum transfer, change in momentum vector, final momentum minus initial momentum. This is momentum transfer. This is just the Fourier transform, nothing else, minus mu r by r. Okay. So, I will do the integral, let us compute the whole thing. Sorry? No, q dot r, kf minus ki. Okay. I think you are right. So, q I should write as ki minus kf. In the final answer it will not matter, but let us correct it. Yeah, you are right. So, q is ki minus kf, but final answer will depend only on q square. So, all right. Now, how do I calculate this? I have to integrate over all coordinates, and q is a vector which is given to us. So, what I do is the following: q vector is given to us, I select z axis parallel to this and x y axis in some way. So, this is my coordinate system and I have to integrate over all r. I can select coordinate axis any way I like, it does not matter, because the expression I am integrating, if I change the coordinate system, the expression will remain same, and therefore, it does not matter, I can choose the axis any way I like. It does not probably help you, this statement. If I tell you when it will change, when I cannot select axis I want. So, suppose the potential depends on theta phi, then I will not be able to select axis the way I want. I will have to write q as q1, q2, q3. Right now, I am going to write q as 0, 0, q. If the potential depends on let us say there is an electric field. So, there is already a direction available to me. So, I cannot arbitrarily select value of q. So, I have to write, select my coordinate axis and keep everything general. In this problem, the potential is mu minus mu r by r. Potential does not tell me any direction. So, I can select any direction, my x axis, y axis, z axis. So, the effect of this is q0 to infinity, we will do it next, and t integral will give you 1 over I q r and exponential of I q r minus e power minus I q r. This term comes from upper limit, this term comes from lower limit. We will get e power I q r t, t lower limit and upper limit. This is what we will get multiplied by 1 over q r when we integrate. So, when we integrate t, we get this answer. So, this answer lower limit and upper limit substitute, you get this. So, 2 pi integral 0 to infinity, the 1 r will cancel, q will come out, I q r dr, I am sorry, yeah, there is something more, e power minus mu r by r. So, that also I have to write here, minus mu r by r. So, we will get that this also will cancel. There are 2 r factors in the denominator and 2 here. So, r goes away, 1 over I q is here, and we have to integrate this I q minus mu into r minus e power minus I q minus mu into r. Now, we have to do integral over r, which is very easy. I have 2 exponentials, I take r common, here also I take r common. So, integral of exponential we know 2 pi by I q 1 over I q minus mu and exponential of I q minus mu r. This is the answer for this, minus e power minus I q minus mu r by minus I q minus mu. So, these are the integrals and r is from 0 to infinity. So, I have to substitute the limits. At 0 the exponential will become 1, exponential will become 1, r equal to 0. At infinity, because I have mu r minus mu r and mu is positive, this will become 0. So, upper limit, this whole thing is 0, lower limit exponentials are 1. So, what you will get is 2 pi by I q and 1 over I q minus mu plus 1 over I q plus mu. Is that correct? Any? There is a minus sign and this one is plus IQ. There is an I sitting here. Okay, let us proceed. I may have made mistakes in sign somewhere. T is 1 and minus 1. I am just checking. I have 1 and minus 1. So, when I put 1, I get the first term. When I put minus 1, I get the second term. I thought this q should cancel. Okay, let us just complete the integral. You can always check and correct the mistakes, okay, if any, because I am going to leave it now. I will not really compare with the other fold scattering. So, we have the answer apart from some maybe some sign mistakes, 2 pi I by q, okay. And then combine the numerator and denominator, you will get q square plus mu square. Numerator, oh, that is what I was looking for, 2 I q. Mu will cancel when you combine the numerator. I wanted q to go away, so this q goes away, I q. So I get 4 pi by, this is correct, q square plus mu square. So this is the answer for matrix element. So we just substitute and get the cross section. All the factors there, they are all constants. So some numbers 1 by q square plus mu square and square of the matrix element. So square here will come. Square of this goes there. Some numbers. You can write down, sit peacefully, write down the numbers carefully and compare with Rutherford cross section by taking mu going to 0 limit. The potential mu r by r becomes 1 by r potential. So you should get Rutherford cross section. Now my question to you is, where are the angles theta phi? Cross section is in terms of scattering angle. So where is the angle theta scattering angle in this expression? This is the final answer. Some numbers 1 over q square plus m square. Does anyone remember how Rutherford formula looks apart from constant? 1 over sine 4 theta by 2. Some numbers I do not care, which will depend on energy and so on, but theta dependence of Rutherford cross section is sine 4 theta by 2. I want to show you that it will come from here. So sigma theta phi has some energy factors, some constants, but finally it has sine 4 theta by 2. I want to know where this theta will come from in all this expression, because this is the final answer. We have to put mu equal to 0. So let us put mu equal to 0. So what are we going to get? We are going to get some numbers, some constants. I am not interested in constants at the moment, q4. So this q4 should give sine 4 theta by 2. Let us see how it will give. What is q? Q is ki minus kf. And what is q square? Q square is ki square plus kf square minus twice ki dot kf. Ki square is twice m E by h cross square. This is related to energy. Initial final energy are same. So another twice m E by h cross square minus 2 modulus of ki modulus of kf into cos theta. This is where the scattering angle will come. So let me write k square. So this is some common value k square. This is also k square. Ki kf modulus also is k square and 2 factor. So we get 2 k square 1 minus cos theta. 1 minus cos theta is 2 k square. Now you see sin square theta by 2, and you square, you get sin 4 theta by 2 from here. Other factors you can write down everything carefully and check that they come out correctly. I do not have time and patience to do that. Okay. But that if you have written all other factors correctly, you will get the other factors also right. those factors will involve energy E square or something, and you can see energy factor coming from here k square. K square will become energy when you square, you will get E square here. H cross will cancel, you have to see where it goes. H cross will cancel when you write k in terms of energy, because classical Rutherford scattering does not have H cross anywhere. And what you get is exact classical Rutherford formula. This is amazing. Quantum mechanics and classical first order approximation is quantum mechanics, first order approximation is giving you exact answers. This is not full calculation of cross section, it is first order and quantum mechanical calculation. That answer is same as classical Rutherford scattering. This is just, I think, a coincidence. Okay. So, this part I will close here. We will go to resonance scattering. I will briefly outline, it is very detailed and very messy. All those messy details I have written up are on internet. Every step has been written up for next thing that I am going to do. So, I will only explain the philosophy, the main points of the method which are used in resonance calculations, and what are we doing, how we are doing, and where it is applied. Only that part we will explain. Details I will leave it for you to read if you are interested. You can go through the result and applications. That will be there in every textbook. So, any questions on this so far? Okay. Now, resonance scattering, let me explain what is that we want to do, where it will be applied and so on. But basic result from perturbation theory will be used. That exact equation I have given, that will be used. That is not from perturbation theory. Just before perturbation theory, I have written an equation. I said it is exact, and we will make approximation from there. Yeah.
Finally, what information does the semi-golden rule embrace? What can we understand from the golden rule? So, in a simpler manner.
Any process you want to calculate, even in quantum field theory, Fermi golden rule is used. So, what kind of process? Decay processes, alpha decay, beta decay, any nuclear reaction, any cross section in potentials. If you give me potential, you want to calculate cross section. In quantum mechanics, you will use Fermi golden rule. Because it is so useful, we call it golden rule. But the formula itself does not have any physical interpretation. It is one term, the way I have written, but the form remains same. There will be higher order corrections, but the form will remain same. It can be written in a similar form, including after higher order corrections. It becomes actually very messy to calculate, do perturbation theory. So, what people do is, they have found other methods which are very efficient and very easy to use. It is called interaction picture. So, that is completely equivalent to perturbation theory, but it is very easy to use. Then one can go further. In field theory, you use Feynman diagrams. You do not do any perturbation theory, you just draw all the diagrams and write the matrix elements. There are rules for writing matrix elements and calculating. But Fermi golden rule is hiding behind everything. When you write those rules, where do you get rules from? That you have to get back to Fermi golden rule and similar things. So when we do a calculation in field theory, anything, x plus y going to b plus c plus d plus anything, x decaying into a plus b plus c anything, any such thing you want to calculate, you will have to use, you use Feynman diagrams and you write the matrix element, and then you have rules for writing the matrix element directly without working out anything. If you work out, you will get the same answer. So you have rules, write the rules, calculate. So particle physics, everywhere it is there. This is what we do. Calculate process, calculate cross section, calculate lifetimes. Okay. So let me explain what is resonance. When I say resonance transitions, I want to apply and I want to see how those things can be calculated. So that is the next topic. I will be brief about it because we are not left with so much of time, but you will get a fairly good idea. You imagine there are systems, there is a system, you can think of hydrogen atom, you can think of particle in a box or harmonic oscillator. It has certain energy levels En and n equal to 1, 2, 3. So I will draw a generic diagram, energy level 1, 2, 3, something. So it has certain energy levels. So there is a system. You can think of hydrogen atom or molecule or anything. Then you have something happening to it, means you put it in an electric field which is changing with time, or magnetic field which is changing with time, or you allow light to fall on it. Light will have electric field and magnetic field changing with that frequency. So basically what we want is that H prime has one frequency and its complex conjugate. So H prime depends on time, and time dependence is simple. It has only one frequency. It is periodic in time and periodicity is given by single frequency. It is not superposition of lots of wavelengths and frequencies, monochromatic light for example. Or when we apply AC, we apply AC of a definite frequency. Okay. So we assume that the Hamiltonian has this form. What is F? F is some operator. We don't know. We don't care right now. So F is some operator, which we can write down if we know what we want to describe. If you want to describe atom in electric field, or if you want to describe a interaction of atom with light, we know how to write H prime. Okay. So there are rules. So F is some operator. Right now for my purpose, this is sufficient. So you have a system and some light falls on it. Light has a particular frequency. So if you calculate first order result, I have already given you the first order result. It looks something like this, the matrix element, and the C, F, first order result, T. I have given you this. I will write the formula again. We can derive this formula from the perturbation method. Same method will apply, but you have to go back a little and calculate. So what was this? We got this answer, first order answer, 1 by I h cross integral 0 to t and f h prime I and exponential of omega f I t dt. This was our first order formula. That's all. this we have derived. Now we are going to take h prime equal to this. So, the whole point is time dependence is only this much, what you see in the exponential and here. So, there will be two terms, one will have 0 to t. Let me write the final answer, then you can see. Suppose I substitute this f, I will get two terms. First term will have omega fi plus omega, second term will have in the exponential omega. So, you will get an answer of this form, which I will write f I f. Plus one more term, one more term multiplied by this, instead of having this sign plus f I, you will have minus sign here in this term, because you have minus I omega t, but otherwise it is same. Now, suppose we change the frequency of external light or whatever it is, omega we change. Omega is coming from external disturbance or light or field that we have applied. So, if you change omega, and if omega fi is plus omega or minus omega, one term will become 0. This will become 0 or the second one will become 0. So, it will become infinite. What does that mean? So, suppose I have, so when omega is plus omega fi equal to 0, there is a problem. This term becomes infinite, or if omega fi minus omega is 0, second term becomes infinite. There is a problem. Infinite is something becoming nonsense. It means you cannot apply your perturbation theory. This is only first order result. So, I cannot use perturbation theory. I have to think what I should do, start all over again. Okay? We do not accept this result. This is nonsense. It tells me my method has failed. First order method will not work. What does this mean? It means if in terms of energy levels, I have two levels. Suppose final energy is more, EF minus EI, and if that is equal to omega, that means external frequency omega matches with this energy difference. So, this is the resonance condition, omega is EF minus EI by h cross. So, anything which is sitting here will come down, that will have large probability, that is all we can say. If this term is 0, then there will be transitions from lower to upper level, they will have large probability. That is all we can say at this stage and nothing more. But what will be the transition probability, how we calculate, we have to go back and have another way of calculating. Numerator, yeah, it is basically undefined. No, it does not work. It does not work. Okay. Let me think more about it. I have not looked at it for a long time, so I cannot answer your question immediately. But basically, the method fails. That is what we are saying. Okay. At best, I can say I have an indeterminate form. Okay. Now, whether anything useful can be done by taking limits, I do not know. Nobody writes anything about it. Everybody says that the method works and we have to do something different, and that gives sensible answers. Okay. So, I will explain the method, and the method is, to understand the method it is very easy, but to calculate it requires several steps. I have given all the details, every step on my notes in zero space. This part is available, and what I am doing is following Landau-Lifshitz. There are maybe different ways of different people may be doing differently, but I am following Landau-Lifshitz. I will explain. To understand that is very easy. So, we go back to an earlier equation which I said is an exact equation. I will write on the board and then I will tell you what approximation we make. So, the idea is to make another kind of approximation and get two equations and solve them exactly. That is the idea. Do not write all the equations and try to do this. Somehow reduce the number of unknown parameters and solve the equations exactly then afterwards. So, the approximation is made at a different level. So, let me remind you of that equation that we derived. What did we do? How did we start on this business? We started with expanding the wave function, full wave function, psi xt, as we wrote this in the form Cn, it depends on time, and psi n of xt. We have written h equal to h0 plus h prime. A psi n are solutions of h0. So, they satisfy this equation. Time dependent Schrodinger equation for h0. This is h0, I am sorry. And they are, the form is known, exponential minus I E n t by h cross times the eigenfunctions of energy. This we have done, and then we derived an equation for Cn. So, that is the equation I am talking about. Before making approximation, we have derived an equation for Cn, which looks like this. D I h cross. So, I will put, you can put anywhere, I h cross here, equal to, there is a summation over all n, and you have exponential of I omega m n t, then you have the matrix element m h prime n, then you have Cn of t sitting there. And how many equations are there? There are infinite equations, 1, 2, 3. For each level, there is an equation. Cm is one coefficient appearing here, and there are all kinds of coefficients. If there are infinite levels, there will be infinite coefficients, and these are infinitely coupled equations. Okay. So, now what we do is, we make an approximation, say that only those two coefficients are involved which in which resonance takes place, like here. Suppose the external frequency is such that it matches with the difference of two levels, E I and E f. Then we throw away all the coefficients and take only m equal to I, n equal to I, m equal to f, and n equal to f. Then I have only two unknown coefficients, and equations are reduced to two equations which are solved exactly. That is a long process. All algebra is, it is all algebra. So, basically what one does is write a f here, and in the right hand side take n equal to f and n equal to I. That is one equation. Write n equal to I here, in the right hand side again take n equal to f and n equal to I. So, you will get two equations for Ci and Cf and solve them exactly. Apply boundary condition, you get the answers. Now, these details are really very long. I have here, I know I am not sure, but basically basic reference for all this is what resonance case is Landau-Lifshitz quantum mechanics. He follows this method. I am not sure what other books do. So, resulting equations, because there are only two unknowns, you can write in a matrix form, 2 by 2 matrix. The equation will look like this. Let me just write one more line. It is very complicated. In the first instance, you will think it is very complicated, but solving them is straightforward. The equation looks like this: d by dt of I h cross C I of t. This is now full coefficient, no approximation, C f t equal to some matrix. This matrix may be complicated, and C I t C f t. Because it is 2 by 2, because it is a matrix equation, you can solve this exactly by diagonalizing this matrix or any other method you want. I will skip details of all this, and I will give you the final answers. And here also, right hand side, when you are writing, keep only those terms which are becoming infinite, in this sense I have described.
Why did you say that matrix is complicated?
No, one has to write everything, exponentials. It is not very complicated, but it does become messy. Details are messy. I have worked out one can keep making mistakes if you are not careful. I have all the details here. I can give you form of the matrix also. Anyway, the final answer is, it may not be very messy to look at it, but to work out it may be messy. Yeah. So, the final answer is, what is that we are looking at? We are looking at transition probability per unit time, and this is what is used in magnetic resonance and such things. You have, let us say, an atom or nucleus, and you put it in a magnetic field. So, the levels will split. So, a particular, you have one particular level, you concentrate the atom or molecule may have several levels, you are concentrating on a particular level. In magnetic field, static magnetic field, not changing with time, apply a time independent magnetic field. This will split into two levels. Now, you want to measure this difference. So, you apply another magnetic field or any time varying field with that frequency. So, this is some B0, this is some B1 with sin omega t, and keep on changing omega t. Then you will, at some time, you will find lot of transitions which you measure by measuring the power absorbed by this system. Whatever, there will be some base which experimentalists will have. Okay, maybe you can comment on that, how this is enough, right? So, you apply on top of a static magnetic field, a magnetic field which has some frequency, keep changing frequency. So, at frequency difference, when this difference matches with this frequency, you will find suddenly some current on some spectrum shoots up, absorption of power or something shoots up. So, that is the resonance condition. So, we want to calculate what happens to that. So, I will just give you the final answer. This thing comes in several places. Okay. So, the final answer for the transition probability, here we calculate transition probability at time t. Okay. So, that answer is nice form. So, this is the frequency with which the transition probability will be changing. This is sin square omega t by 2. And what is nu? Nu is basically nu equal to 0 is the residence condition. So, nu is something like EF minus EI minus h cross omega by minus by h cross. So, when nu is 0, that is the resonance condition. So, this is the final answer. I will stop here. It has, as I said, lots of applications, all magnetic resonance, all kinds of things are there. In particle physics also it has applications, neutrino oscillations, right? We will use something like that? Not exactly. Yeah. Yes. It will change flavor. Yeah. Okay. We don't have time to discuss this formula in detail, and I have not planned it that way because I knew we will not be left with time. So, I have not planned a discussion. Books will discuss. This has a name, right? Rabi's formula, right? Or Rabi's oscillations, it gives you. Yeah, omega is the Rabi frequency, right? So, I will stop here. Any questions, please ask, otherwise we close this topic.
There is a very interesting story about Rabi's work.
Huh.
Incidentally, I have listened to his lecture.
I see. Okay. Okay.
When he actually flip shots like labs and so on,
They will not convince. They